detection of an element other than hydrogen in the universe. The results have been accepted for publication in the journal Astronomy and Astrophysics, and a preprint version can be found on ARQBio. As co-author Roberto Maiolino, a professor of experimental astrophysics at the Kavli Institute for Cosmology at the University of Cambridge, said in a statement, "Earlier research suggested that carbon started to form in large quantities relatively late, about 1 billion years after the Big Bang, but we found that carbon formed much earlier. It might even be the oldest metal of all." Astronomers classify elements heavier than hydrogen and helium as metals. That's because, aside from hydrogen and trace amounts of lithium, these elements were forged inside the fiery furnaces of stars and distributed throughout the universe by star explosions called supernovas. This process of heavy element production and seeding was once thought to take many star lifetimes before elements heavy enough to form planets were widely available. But new discovery made by James Webb has challenged this preconception. What James Webb found in the remote galaxy known as GSAZ-12, which was 100,000 times less massive than the Milky Way, were traces of oxygen and neon mixed with a strong signal of carbon. Exactly how carbon could have formed so early in the universe's life is unclear, although it could be due to stars collapsing with less energy than initially thought, according to the researchers. As carbon would have formed in the star's outer shells, this could have enabled it to escape and seed the early universe sooner than expected, instead of being sucked inside the black holes formed from the collapsing stars. That means it's not necessarily true that life must have evolved much later in the universe. Perhaps life emerged much earlier. Perhaps somewhere, under some conditions we might even consider too exotic for life. There are living creatures completely unlike us, better suited to surviving, thriving, and building an interstellar civilization in the cosmos. Perhaps they're not made out of familiar ingredients like proteins, but something else entirely, like a crystalline or metallic set of structures. At that point, it simply becomes a game of hide and seek. Is anybody out there? This ancient question, now known as the Fermi paradox, has haunted us for ages, in particularly as humanity casts an ever wider net across the cosmos, capturing evidence of thousands of worlds. The good news? We know vastly more than any previous generation. Our galaxy is crowded with exoplanets, planets around other stars. A healthy percentage of them are small, rocky worlds of a similar size and likely similar composition to our home planet. The ingredients in the recipe for earthly life, water, elements associated with life, available sources of energy, appear to be almost everywhere we've looked. Now the bad news. We have yet to find another Earth with life, intelligent or not. Observing signs of possible microbial life in exoplanet atmospheres is currently just out of reach. No convincing evidence of advanced technology, artificial signals by radio or other means, or the telltale sign of, say, massive extraterrestrial engineering projects, has yet crossed our formidable arrays of telescopes in space or on the ground. And finding non-intelligent life is far more likely. Earth existed for most of its history, 4.25 billion years, without a whisper of technological life, and human civilization is a very late-breaking development. Is there life beyond Earth? So far, the silence is deafening. While the chances of finding life elsewhere remain unknown, the odds can be said to be improving. A well-known list of the data needed to determine the likely abundance of life-bearing worlds, though highly conjectural, is known as the Drake equation. Put forward in 1961 by astronomer Frank Drake, the equation is one of astronomy's most famous attempts to answer the question not just about life, but about the top-shelf stuff. Intelligent life with the ability to communicate with beings outside their planet. Microbes or floating sentient clouds don't make the cut. We want aliens that will talk to us. To be clear, this means there could be life out there in the universe that the Drake equation would discount. But in terms of knowing how likely we are to receive alien signals, it's a great way to organize our questions. It starts from a sky-high view of the necessities for life, and then zooms in, each component of the equation narrowing or broadening the possibilities and getting harder to determine. The equation asks first about the average rate of star formation in the galaxy. This doesn't sound particularly applicable to life, but that's the beauty of the Drake equation. It realizes that to have a species, you have to have a planet, and to have a planet, you must have stars. So, we'll start with making stars. For a long time, this was the only number we had hard evidence for. We can measure star formation rates in many galaxies, ours or any other, by looking at the fraction of young to old stars. We also need to understand something called the initial mass function, which explains how many big, little, and in-between stars emerge out of a stellar nursery. This number ends up being a couple, or 1.53 stars born per year, according to the most recent science. This may not sound like much on the face of it, but keep in mind the billions of years the universe has been churning. It adds up quickly. The second number is the fraction of stars that have planets. This was a mystery for a long time. Astronomers could speculate, but until the past few decades, we really didn't have solid evidence. Thanks to Kepler and WASP and all the other exoplanet surveys, we now have a lot of planets and star systems to judge from. Our best guess for this number is roughly 1. That is, there's roughly 1 planet for every star in the galaxy. Of course, some stars, like our own sun, have many planets, and others none, but we're talking averages here. The next question is, once a star has planets, how many of them are capable of supporting life? This is where we start hitting roadblocks. We only know of 1 planet that does have life. We can argue about whether Mars could have in the past. We can define habitable zones where planets can support liquid water on their surfaces. But what about worlds like Europa, with subsurface oceans? What about tidally locked planets around dwarf stars? The number is highly variable. We think it's somewhere between 3 and 5 right now, but that could be higher or very much lower, depending on how you define habitability. And then we start really plunging into the unknown. What fraction of planets that could support life actually develop living creatures? Again, we know of just 1 so far that has. This number is very much an unknown. Is this 100%? Or do we count Titan and Europa and Mars and Venus and say it's only 20% in our solar system? Past this, what fraction of planets with life host intelligent life? Possible good luck here. 100% of the planets with life we know of have intelligent life. On the other hand, out of the millions of species that have existed in Earth's history, only 1 of them has achieved sentience. So maybe the odds are not so great. Maybe there are a lot of planets with giraffes, but none others with humans. This next bit is part of what separates the Drake equation from general thought experiments about the existence of life in the cosmos. It asks how many intelligent civilizations come up with technology that lets them broadcast evidence of their existence into space, purposefully or not. We've been sending out radio waves for decades, and we're only getting louder. It's of course possible for an intelligent civilization to remain quiet, but we're interested in the ones we can communicate with, which means they have to give some signs. The last factor considers how long these civilizations hang around. One that exists for only 10 years before an asteroid destroys it, or destroys itself by nuclear war, will be harder to find than one that broadcasts for hundreds, thousands, or even millions of years. During the Cold War, many argued that it looked like our civilization, and therefore most others, might not make it past the nuclear age. The window between developing radio technology and nuclear weapons was pretty brief for us. On the other hand, you can argue that once a life form escapes off-world and starts to colonize other planets, it becomes much harder to wipe out as an entire civilization. One asteroid or plague wouldn't do it. So maybe those civilizations quickly become immortal. If you combine all these numbers, you can end up with conservative estimates that give a total number less than 1, as in, we are alone in the universe. More optimistic numbers can yield tens of millions of possibilities. Drake's original estimates were between 20 at the low end and 100,000 at the upper end. So, while we're making progress on some of these figures, we've still got a long way to go. Thus, while Drake's list can be a good conversation starter and a useful way to frame the complex questions around the possibility of other life, these days, scientists don't spend a great deal of time discussing it. Instead, they use a narrower yardstick, the habitable zone. Either way, if you want to have life arise in the universe, a planet might not be absolutely required, but it certainly provides an outstanding environment where life's emergence is greeted by a slew of friendly conditions. That means that a certain amount of chemical enrichment, that is a great enough fraction of elements heavier than hydrogen or helium, needed to have been created prior to the formation of the star and stellar system you're looking at. Back in 2022, the total confirmed exoplanet tally passed 5,000 for the first time, and a remarkable set of facts emerged from analyzing which stars had planets around them at all. Almost all of the planets, 98.2% of them, were found around stars that had at least 25% of the heavy element content found in the Sun. The remaining 1.8% of the planets were found around stars that had between 5% and 25% of the Sun's heavy element content, and that no planets at all were found around stars with fewer than 5% of the heavy elements found in the Sun. If you want to have a rocky world that gives life a habitat for surviving and thriving, we need to have enough heavy elements present, and that places restrictions on where, in the evolved galaxies throughout the modern-day universe, such planets are capable of forming. Planets provide the raw elements from which biochemical reactions become possible for life, but another needed ingredient for life's emergence is a source of energy. While a star might not be the only possibility for providing such a source, as radioactive decay, tidal forces induced by a parent planet or large moon, volcanic activity, and other internal and external sources are all plausible, we know that the Sun provides the energy that powers nearly all forms of life on Earth. However, choosing to have a star power the life on a world, however, places enormous restrictions on the types of life-friendly worlds that can arise. For one, you have to have a good location relative to your star. If you find yourself too close to your parent star, the overwhelming heat, winds, and radiation coming from the star will do things like strip the atmosphere away, or heat the surface up to the point where the only liquids that can exist on the world's surface are lava-based. Similarly, if you find yourself too far from your parent star, you'll be too cold and receive too little energy from the star for life to exist on the surface. That's the idea behind what astronomers and astrobiologists call the habitable zone, which describes where, given an Earth-like atmosphere, liquid water will be possible on the planet's surface. Every star's habitable zone is unique, determined by the star's temperature and luminosity, its overall energy output. The brighter your star is intrinsically, the wider and more distant from the star the habitable zone will be. The cooler and fainter your star is, intrinsically, the narrower and closer to the star its habitable zone will be. In our own solar system, the habitable zone is thought to extend inward from Earth's orbit to just slightly farther out than Venus's distance from the Sun, but outward to right about where Mars is located, and perhaps just a little bit farther. Many scientists believe that if Mars were just a fair bit larger and more massive, it may have been just as suitable for life as Earth is, even over long periods of time. However, this poses a big difficulty for stars that are more massive than the Sun. You see, planets require time to cool down once they initially form in order for life to arise on them. A world covered in volcanic activity, where the only oceans are boiled away into the atmosphere, are not exactly what one would call life-friendly, at least based on our current understanding of life. But for stars, the total stellar lifetime is also dependent on the star's mass, which is intimately linked to its intrinsic brightness. This means that stars with more than about 150% the mass of the Sun may not provide good locations for life to arise and sustain itself at all. There's an old saying that goes, "The flame that burns twice as bright lives just half as long." But for stars, the situation is far, far worse than that. The more massive your star is, the more fuel it has in its core to produce nuclear fusion. And so it's no surprise that more massive stars shine brighter than their less massive counterparts. But what's perhaps surprising is that the more massive your star is, the greater the maximum temperature in its core, the larger the core's volume, where nuclear fusion can occur at temperatures exceeding $4 million K, and the faster it burns through the nuclear fuel located within its core. When you add all the cumulative effects together, what you find is that a star that's twice as massive as another lives just 1/8, about 12%, as long. Furthermore, stars evolve over their lifetime by heating up, meaning that any inhabited planet only has a finite amount of time over which it can support life, before its parent star heats up so severely that its oceans boil away and any biological activity gets sterilized. On planet Earth, we probably have about another 1–2 billion years before that occurs. But on a planet around a significantly more massive star, any life that formed would have been sterilized long before it could have evolved into something complex, differentiated, and intelligent. Planets around more massive stars simply run out of time. But this might make less massive stars even more attractive candidates for life, long-term, than stars like our Sun. This might sound counterintuitive at first, because planets around the longest-lived stars, the low-mass ones that fall into the M class, according to astronomers, also known colloquially as red dwarf stars, face two major problems that aren't present on a planet like Earth, which orbit around Sun-like G-class stars. Stars that are lower in mass than the Sun might live for hundreds of billions or even trillions of years, with the lowest mass stars of all persisting for up to 100 trillion years. These two problems they face are significant, but still might not be deal-breakers for life. The first one is tidal locking. The distance from a more massive parent body, like a star, to the less massive orbiting body, like a planet, determines the timescale over which the less massive body becomes tidally locked to the more massive ones. Tidal locking is what happened to the Moon orbiting the Earth, and explains why one side of the Moon, the same side, always faces the Earth. Around M-class stars, all planets within what we call the habitable zone will become locked in only a few million years, tops, meaning that they'll always have one scorching hot side that always faces their star and one freezing cold side that never receives direct light from their parent star. There are plenty of planetary scientists who think that this tidal locking disfavors life, as it creates a severe and permanent temperature gradient across the planet, which only spins on its axis once per orbital revolution. However, tidal forces on the planet will heat the planetary core, which could enable the production of a not necessarily needed protective magnetic field, and lead to more volcanic outgassing, which could prevent the atmosphere from being stripped away, and whereby atmospheric circulation could enable liquid water and possibly life, not just in a narrow ring along the day-night border, but in regions extending well onto both the day and night sides. In other words, this tidal locking, while it might seem unusual to us here on Earth, might not be a blocker to life arising and thriving. However, there's also the second major problem that planets around lower mass stars must contend with. This problem is related to flaring activity, and it is serious. Whereas a star like our Sun is only extremely slightly variable, with its energy output increasing by only a few percent every billion years and changing by no more than 0% over even the extremes of the solar cycle, all of the low-mass stars we've observed remain tremendously active and variable, even billions of years after their birth. Red dwarf stars have star spots similar to sunspots that are enormous and can cover up to half of the star's area. Despite emitting much less light than the Sun, They frequently emit energetic, X-ray, and ultraviolet-rich flares, all capable of stripping and orbiting planets' atmosphere away. Many have conjectured that this type of stellar activity renders these planets completely uninhabitable. But there's an important caveat there, for the time being. You see, our sun and all stars were once like that too. Active, flare-rich, and frequently emitting ionizing and atmospheric evaporating radiation and particles. But over long enough timescales, a star like our sun settles down into a more stable phase, allowing a steady dose of radiation that hardly varies in temperature or intensity to strike any orbiting planet, what we know and think of as a set of conditions friendly to life. It turns out that the amount of time it takes a star to settle down depends on the star's mass. K-class stars, the class in between a G-class star like our Sun and an M-class red dwarf star, may require hundreds of millions or even billions of years to settle down into a stable phase. But we've seen the older K-class stars reach this state of steady emission. For red dwarf stars, we fully anticipate that someday. But on timescales longer than the present 13.8 billion year age of the universe, those stars will reach a stable phase as well. Even if they strip an orbiting planet's atmosphere away early on, volcanic activity can replenish it, leading to the possibility that life will arise on such a world well into the far future, many trillions of years from now. However, at some point, a long time from now, stars will cease to form. The rate of star formation across the universe has been dropping ever since its heyday 11 billion years ago, and now sits at right around 3% of its maximum, while continuing to fall. Once a galaxy has lost all of the gas within it, it no longer has material capable of forming the next generation of stars, and so the highest mass, shortest-lived stars all begin dying away with time. After a few billion years have gone by, only the lower mass, redder-colored stars remain, and these galaxies become known as red and dead. Massive galaxies near the centers of large galaxy clusters become red and dead the fastest, while isolated gas-rich galaxies will last the longest, engaging in what's known as quiescent star formation for up to trillions of years to come, or possibly longer. In the locations where star formation only proceeds slowly, at a trickle, rather than in massive bursts, it's possible that those gas-rich galaxies will keep on forming stars for up to quadrillions of years. Even once that stops completely, there will be one final set of objects that merges to light up the cosmos for the last time, brown dwarfs or failed stars that eventually inspiral and merge. When they get there, if their mass is sufficient, they can ignite fusion to form a red dwarf. And if the planetary conditions on any orbiting worlds are just right, life might arise and thrive once that star has settled into the stable phase of its life. All of this means, when we put the pieces of the puzzle together, the following opportunities for life. For the stars that exist today, the lowest mass ones will become habitable only after hundreds of billions or even trillions of years have passed, and may remain habitable for up to Shakt 10 to the power of 14 or 100 trillion years. For the stars that haven't formed yet, it's possible that new star formation will bring with it new chances for life, extending up to Yun 10 to the power of 17 or 100 quadrillion years into the future. And for the stars that will eventually form from the mergers of brown dwarfs, they may continue igniting for up to 10 to the power of 21 or 1 sextillion years into the future, before gravitational interactions remove what we think of as galaxies from the picture entirely. All of this comes along with a great deal of uncertainty and unknowns. After all, Earth, even in 2024, remains the only world we know of where life has ever arisen and continues to thrive. The possibilities for life, at least as we understand it, remain varied and ubiquitous, and should be plausible even far into our universe's cosmic future, even if our cosmic home won't be habitable for much longer. In a universe with so many worlds and so many biochemical possibilities, past, present, and future, It would be foolish to assume that the way things unfolded here represent the only reasonable pathway to success. And in the quest of alien hunt, there are some worlds that we've discovered that, scientists believe, may contain alien life and which we could inhabit. Here is a fresh brief. 1. Kepler 186f. One of the most likely candidates for life as we know it is Kepler 186f. In fact, this is a planet that if we could get there, we might be able to colonize with relative ease. Sadly, the world is 490 light-years away, so even using very liberal and generous estimates, it would take us hundreds of thousands of years to reach. The planet was discovered back in April of 2014, just about a year ago. This falls well into the category of potentially Earth-like planets, as it is within the habitable zone of its star, is terrestrial, and is just 10% larger than Earth. Ultimately, Kepler 186f is just the outermost of the 5 known planets in the Kepler 186 system. Kepler 186 is a red dwarf star, which means that it is considerably smaller and dimmer than our own Sun. The Planetary Habitability Laboratory even created an excellent comparison of a Caribbean sunset as it appears on Earth, and how a similar spot might look if it were on Kepler 186f at dusk. 2. Kepler 283c. Kepler 283c was discovered along with a host of other worlds as part of an enormous data dump from the Kepler Space Telescope. This data contained a staggering 700 newly confirmed exoplanets. Keep in mind, just 20 years ago, we didn't know of any planets in other solar systems, so 700 in one go is quite staggering. However, this world is on the border of being able to support Earth-like life. It is about twice the size of Earth and orbits much closer to its home star, which is over 1700 light-years from Earth. But again, due to the decreased size in the star, it is still well within the bounds of Kepler 283's habitable zone. 3 and 4. Gliese 667c, F and 667c, E. Gliese 667cf and Gliese 667c. E would offer an amazing view. Why? They have 3 suns. Because this is a triple star system, these are 2 of the strangest, potentially habitable worlds that we've ever discovered. Like the other worlds covered, both planets fall inside their star's habitable zone, and at just 22.1 light-years away, it would still take some time to get there, but the travel would be a tiny bit more manageable. 5 and 6. Kepler 62e and Kepler 62f. As their names suggest, these Kepler 62 planets are some other worlds that were discovered by NASA's Kepler Space Telescope. These planets would give us a little more room to work with, as 62e is about 1.6 times more massive than Earth, and 62f is just about 1.4 times as massive. These worlds are quite out there, at least as far as our ability to travel goes. They wander through space about 1,200 light-years from Earth in the constellation Lyra. And if you were born on 62e, you would be quite a bit older than you are now. It completes 1 lap around its parent star, which is a red dwarf, every 122 days. 67f has an orbit of some 267 Earth days. Researchers think that both 62m and 62f are water worlds, warm places mostly or completely covered by liquid water. So they would also be absolutely awesome to visit. Imagine how big the whales may be here. But living there long-term might be a bit difficult. 7. Gliese 581d. Gliese 581d is another one of our galactic neighbors in the grand scheme of things. It is basically just around the corner. This world is just 20 light-years away, the closest planet covered on this list. However, despite its close proximity and its location in its star's habitable zone, the planet might have a thick carbon dioxide atmosphere. This would make it rather inhospitable, as we need to breathe oxygen. However, scientists also believe it could be rocky with liquid water. So, although it might not be too grand for us, scientists think that it could harbor stunning rainforests. But even if it does have oxygen, humans would find it a little difficult to thrive there, as it is some 7 times more massive than Earth and about twice its size. Still, since it is essentially in Earth's backyard, we might want to make a go at it anyways if we ever get the tech to utilize interstellar travel. Last, remember that when you watch this video, somewhere in space, the James Webb Space Telescope is observing the TRAPPIST-1 system and its 7 Earth-sized planets, with 3 in the habitable zone of their star. It will take time to collect enough light and analyze the data, but we truly live in an amazing time, where we can for the first time ever collect light from a small, rocky world in the habitable zone of another star and analyze it for signs of life. In other words, we are on the verge of finding out the answer to the 1,000-year-old question: are there other alien Earths out there? Look up into the stunning sky. Find your favorite star and allow yourself the freedom to wonder. What if we are not alone in the cosmos? That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. For as long as humanity has looked up at the stars, we've wondered about the origins of the universe. How did everything come into existence? For decades, the Big Bang Theory provided a satisfying answer. This powerful explosion, which took place around 13.8 billion years ago, is thought to have set in motion the expansion of the universe as we know it. But now, with the launch of James Webb, a new frontier in space exploration opened up, and with it, an unsettling glimpse into what may have occurred before the Big Bang itself. The revelations have shaken the scientific community and sparked profound existential questions about the nature of reality and the universe we inhabit. Join us as we dig deep into how James Webb just unlocked the biggest cosmic mystery. For decades, the Big Bang Theory stood as the cornerstone of cosmology, offering a comprehensible narrative of how the universe came into being. According to this theory, about 13.8 billion years ago, the universe began as a singularity, an infinitely dense point that contained all the matter and energy of what would become the universe. This state was unstable, leading to a massive expansion we call the Big Bang. Contrary to popular belief, this wasn't an explosion in space, but rather the rapid expansion of space itself. In the first tiny fraction of a second after the Big Bang, the universe was a seething hot mass of particles and energy. The 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate. This period is often referred to as cosmic inflation, where the universe expanded exponentially, smoothing out space and setting the stage for galaxies and stars to form. As the universe cooled, particles like quarks and gluons began to form protons and neutrons, which later combined to create atoms. Hydrogen and helium, the lightest elements, emerged about 300,000 years after the Big Bang during a period called recombination, when the universe became transparent to light. The leftover radiation from this event is known as the cosmic microwave background, which we can still detect today. Over the next billions of years, gravity pulled together clouds of hydrogen and helium, forming the first stars and galaxies. Inside stars, nuclear fusion created heavier elements like carbon, oxygen, and iron. When massive stars exploded in supernovae, they scattered these elements across space, seeding future generations of stars, planets, and eventually life as we know it. However, despite its widespread acceptance, the Big Bang Theory has always been haunted by unresolved questions. As told, at the heart of the Big Bang Theory is the concept of a singularity, a point where the laws of physics as we understand them break down. This singularity represents an infinitely small and dense state from which the universe is said to have emerged. However, the idea of a singularity itself presents profound challenges. The notion of infinite density and zero volume defies our conventional understanding of space and time, suggesting that our current physical theories, including general relativity and quantum mechanics, are incomplete. And one of the most tantalizing questions that arise from the Big Bang theory is what caused the Big Bang? What existed before it? Was there even a before, given that time and space supposedly began at that moment? While these questions have been largely theoretical, recent findings from the James Webb Space Telescope have given us new and deeply disturbing clues. Launched in December 2021, the Webb telescope has been equipped with cutting-edge infrared capabilities, allowing it to peer deeper into the cosmos than any previous telescope. Where the Hubble Space Telescope could only glimpse at faint traces of distant galaxies, James Webb can capture the earliest light emitted by the first stars and galaxies, giving us an unprecedented view into the very fabric of space-time. But Webb's capabilities extend beyond simply observing early galaxies. It can also capture data about the universe's structure, composition, and evolution in ways previously unimaginable. As scientists analyzed the data streaming in from Webb, they began to notice something peculiar, something that didn't fit within the framework of the Big Bang theory. One of the most stunning discoveries made by James Webb is its detection of structures in the early universe that should not, by all accounts, exist. Observing galaxies that are thought to have formed just a few 100 million years after the Big Bang, astronomers have encountered mature, well-organized galaxies that challenge our understanding of cosmic evolution. These galaxies seem far too old and complex for the timeline provided by the Big Bang model, which suggests that the early universe should have been a chaotic, turbulent place, with galaxies still in their infancy. What's even more alarming is Webb's observation of faint cosmic ripples, traces of energy that seem to date back to a time before the Big Bang. These ripples could be the remnants of a pre-existing universe, something that existed before the event we've come to understand as the beginning of time itself. If this is the case, it suggests that the Big Bang may not have been the true beginning, but rather a transition, a new phase in an eternal cycle of cosmic destruction and rebirth. What's notable, the idea that there might have been something before the Big Bang is not entirely new. Various theoretical models have posited the existence of a multiverse, suggesting that our universe is just one of many universes, each with its own physical laws and properties, in a vast multiverse. In this model, the Big Bang could have been the result of a local event in a larger multiverse, with other universes constantly being born through similar processes. This could involve mechanisms like eternal inflation, where different regions of space experience continuous cosmic inflation, each giving rise to a new universe. The multiverse concept offers the possibility that before the Big Bang, there were other universes or cosmic regions that existed and gave rise to our own. Another theory is the idea of a cyclic universe, where the universe goes through infinite cycles of expansion and contraction. In this model, the universe could have experienced multiple Big Bangs and Big Crunches. After expanding for billions of years, the universe could collapse back into a singularity, the Big Crunch, only for another Big Bang to occur and begin a new cycle. This concept has been explored in various forms, from ancient cosmological ideas to modern versions like conformal cyclic cosmology, proposed by physicist Roger Penrose. However, Webb's data brings a disturbing new dimension to these theories. If the faint cosmic ripples it has detected are indeed traces of a pre-Big Bang universe, then we are faced with a chilling possibility. The universe may be caught in an endless loop of destruction and renewal, where everything that exists is destined to be obliterated, only to be reborn again in a new form. This raises questions about the very nature of existence. Are we living in a universe that is fated to collapse, with all matter, life, and consciousness erased, only to be replaced by something else? The concept of eternal cycles of cosmic death and rebirth may sound philosophical, but Webb's observations lend it a disturbing degree of scientific credibility. We may be part of a universe that is not unique or special, but merely one in an infinite series, with countless others having come before and countless more to follow. The realization that our universe, and by extension, everything within it, is impermanent, subject to a cosmic reset, is nothing short of terrifying. One of the most unsettling aspects of Webb's discoveries is the suggestion that time itself may not be linear. According to our current understanding of physics, time began with the Big Bang. But if there was something before it, what does that say about the nature of time? Some theorists have begun to speculate that time might be cyclical rather than a straight line. In this scenario, the concept of before and after becomes meaningless, and the universe may be in a perpetual state of becoming, constantly evolving through an infinite loop. From the moment we are born, our understanding of reality is deeply intertwined with the flow of time. We sense its passage as a series of events, moving from the past through the present into the future. However, this perception is not necessarily an accurate representation of how the universe operates. In the early 20th century, Albert Einstein revolutionized our understanding of time with his theory of relativity. He demonstrated that time is not a constant, as Isaac Newton had previously assumed, but is flexible and relative, depending on the observer's velocity and the presence of massive objects. This discovery revealed that time and space are woven together into a four-dimensional fabric known as spacetime. This means that time does not flow uniformly for all observers. A clock on Earth, for example, runs at a slightly different rate than a clock on a satellite in orbit. The faster you travel, the slower time passes relative to someone at rest, a phenomenon known as time dilation. Yet, relativity still treats time as something that exists, even if it is flexible and malleable. More radical ideas suggest that time might not exist at all, at least not in the way we commonly experience it. In quantum mechanics, the very nature of time becomes even more puzzling. Quantum mechanics deals with the behavior of particles at the smallest scales, where the classical rules of physics break down. In this realm, particles can exist in multiple states simultaneously, and their behavior can be described only probabilistically. The concept of time in quantum mechanics is particularly problematic. At the quantum level, time often appears to be irrelevant. When physicists describe systems of particles using equations such as the Schrödinger equation, time is just another variable, treated symmetrically with space. This is in sharp contrast to our everyday experience, where time seems to move in one direction only, from past to future. In quantum mechanics, the fundamental laws of physics are time reversible, meaning that they do not distinguish between past and future. This suggests that time's arrow, the irreversible flow of time that we experience, might not be a fundamental feature of reality, but instead an emergent property. The concept of time in quantum mechanics becomes even more complicated when we consider entanglement, a phenomenon in which two or more particles become linked in such a way that the state of one particle is instantaneously correlated with the state of another, no matter how far apart they are. This spooky action at a distance, as Einstein called it, challenges our understanding of both time and space. In entangled systems, the flow of time seems to become irrelevant. The relationship between particles does not depend on a linear sequence of events, suggesting that time might be less fundamental than previously thought. One of the most intriguing theories that challenges our conventional understanding of time is the block universe theory, also known as eternalism. This idea arises from Einstein's theory of relativity and suggests that time is not something that flows, but rather a dimension in which all events, past, present, and future, coexist simultaneously. In the block universe, the passage of time is an illusion created by our limited perspective. Imagine time as a landscape. When we stand at one point on this landscape, we experience that moment as the present. However, from a higher dimensional viewpoint, the entire landscape, the past, present, and future, is laid out all at once. Just as all points in space exist simultaneously, all points in time exist simultaneously. The past is not gone, and the future is not yet to come. They are simply parts of the space-time continuum, existing as part of a larger, unchanging whole. If the block universe is correct, then time does not flow in the way we perceive it. Our experience of time might be similar to watching a movie. We see the frames one after another and perceive motion, but in reality, the entire film exists at once. Our consciousness might be moving through time in a similar way, experiencing moments sequentially, even though they all coexist in the space-time block. Despite these radical ideas about time, we still experience the world as a sequence of events. A glass shatters, but it does not spontaneously reassemble. Ice melts, but does not freeze on its own. This irreversibility of time, the so-called arrow of time, is deeply rooted in the laws of thermodynamics, particularly the second law, which states that entropy, a measure of disorder, in a closed system always increases over time. Entropy provides a direction to time that seems absent in the fundamental laws of physics. While the equations governing the universe at a microscopic level are time-reversible, meaning they could work equally well if time ran backward, the second law of thermodynamics introduces a preferred direction, from lower entropy to higher entropy. This gives rise to the arrow of time that we experience. However, some physicists argue that the arrow of time may itself be an emergent phenomenon, rather than a fundamental aspect of the universe. It could arise from the initial conditions of the universe, particularly the extraordinarily low entropy state at the moment of the Big Bang. If this is the case, then the arrow of time might be a consequence of the universe's birth rather than a fundamental feature of reality. This again raises the possibility that time, as we experience it, is not fundamental, but rather a product of the specific conditions of our universe. Philosophically, the notion that time may be an illusion has profound implications for our understanding of consciousness and existence. If time does not exist as we perceive it, then what does it mean to be conscious in a world where past, present, and future are indistinguishable? Some philosophers and neuroscientists suggest that our perception of time is closely tied to the way our brains process information. The brain constructs a continuous stream of consciousness by piecing together discrete moments of sensory input, much like a film projector creates the illusion of motion by rapidly displaying still images. In this view, time may be a mental construct, a way for our brains to make sense of the universe. Just as we perceive colors that do not exist outside our minds, color is merely the brain's interpretation of different wavelengths of light, we might perceive time as a flow when it is, in fact, static. This idea is bolstered by research into altered states of consciousness, such as meditation, psychedelic experiences, and certain neurological conditions, in which individuals report a breakdown of the usual perception of time. In these states, people often describe a sense of timelessness, or the feeling that past, present, and future are all one. Such experiences suggest that our perception of time is flexible and can be altered, reinforcing the idea that time might be a mental construct. Ultimately, the question of whether time is an illusion touches on some of the deepest mysteries of existence. If time does not exist as we perceive it, then our understanding of reality, causality, and even the nature of life and death might need to be re-evaluated. Time, in this view, could be akin to a trick of the mind, a useful but ultimately flawed way of organizing our experiences. Physicists continue to wrestle with the concept of time, seeking something called a theory of everything. Some suggest that such a theory might reveal that time, as we understand it, does not exist at the most fundamental level of reality. If this is true, then the implications for our understanding of the universe and our place in it are staggering. But what exactly is a theory of everything? Well, put simply, a theory of everything would encompass all the fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Today, we have two primary frameworks that describe these forces: general relativity, which accounts for gravity and large-scale structures like stars and galaxies, and quantum mechanics, which explains the behavior of particles at microscopic scales. However, these two theories are fundamentally incompatible. General relativity sees space and time as continuous, while quantum mechanics treats them as quantized and probabilistic. Bridging this gap is the central challenge for a theory of everything. Albert Einstein's general theory of relativity, formulated in 1915, revolutionized our understanding of gravity. In Einstein's view, gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time. Massive objects like stars and planets warp the fabric of space-time, causing other objects to move in response to that curvature. This insight replaced the Newtonian idea of gravity as a force acting at a distance and explained a variety of phenomena that Newtonian mechanics could not, such as the precise orbit of Mercury and the bending of light around massive objects, gravitational lensing. General relativity has been incredibly successful in describing large-scale phenomena, such as the dynamics of galaxies and the expansion of the universe. However, it breaks down at extremely small scales, particularly in describing the center of black holes or the conditions of the universe just after the Big Bang. At these scales, quantum effects become significant, and general relativity alone cannot provide a complete picture. Quantum mechanics, developed in the early 20th century by scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, provides a detailed description of the interactions between subatomic particles. Unlike general relativity, quantum mechanics deals with probabilities rather than certainties. The behavior of particles is governed by wave functions, which describe the probability of finding a particle in a particular state. This probabilistic nature is fundamentally different from the deterministic view of space-time in general relativity. One of the triumphs of quantum mechanics is the standard model of particle physics, which unifies three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. The standard model successfully describes a wide range of particle interactions and has been confirmed through countless experiments. However, it does not include gravity, the fourth fundamental force, nor does it explain certain cosmological mysteries, such as dark matter and dark energy. The biggest obstacle to a theory of everything is gravity. While general relativity beautifully explains gravity at large scales, it doesn't work at quantum scales. When physicists try to apply quantum mechanics to gravitational fields, they encounter infinities, mathematical quantities that make no physical sense. This issue becomes especially critical in extreme environments, such as black holes, where both quantum effects and gravitational effects are significant. The mathematical incompatibility of gravity and quantum mechanics suggests that we are missing a deeper theory that can unify them. Physicists believe that gravity must have a quantum description, but no one has yet found a consistent theory that works in all situations. This has led to the search for new ideas, such as quantum gravity, which could unify general relativity and quantum mechanics under one framework. One of the most prominent attempts to develop a theory of everything is string theory. In string theory, the fundamental building blocks of the universe are not point particles, as in the standard model, but rather tiny, vibrating strings. These strings can vibrate in different ways, and the different patterns of vibration correspond to different particles. In this framework, gravity emerges naturally as one of the vibrational modes of the strings, thereby incorporating gravity into a quantum framework. String theory also introduces the concept of extra dimensions. While we are familiar with 3 dimensions of space and 1 dimension of time, string theory suggests that there may be additional hidden dimensions that are compactified, curled up so small that they are imperceptible to us. These extra dimensions could help explain why gravity is so much weaker than the other fundamental forces, as it may be spread out over these additional dimensions. However, string theory is far from proven. One of its major criticisms is that it is not experimentally testable in any practical sense. The energy scales required to probe the structure of strings are so high that they are beyond the reach of current or foreseeable technology. This has led some physicists to question whether string theory is truly a scientific theory, as it currently lacks the ability to make falsifiable predictions. Another approach to unifying gravity and quantum mechanics is loop quantum gravity. Unlike string theory, which attempts to replace point particles with strings, loop quantum gravity works directly with the fabric of spacetime itself. It proposes that spacetime is quantized at the smallest scales, forming a network of discrete loops. These loops form a kind of atomic structure of space, similar to how matter is made up of atoms. Loop quantum gravity has had some success in explaining certain phenomena, such as the behavior of black holes and the Big Bang. However, like string theory, it is not yet complete, and much work remains to be done before it can be considered a viable theory of everything. Any theory of everything must also account for 2 of the biggest mysteries in modern cosmology: dark matter and dark energy. Dark matter is one of the most critical ingredients in the universe, but it's something we cannot directly observe. It doesn't emit, absorb, or reflect light, which makes it invisible to telescopes. Instead, its presence is inferred through its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, many of the structures we see in the universe today, from galaxies to massive clusters of galaxies, would not have formed. The first hint of dark matter's existence came in the 1930s when Swiss astronomer Fritz Zwicky observed the Coma cluster, a collection of galaxies. Zwicky noticed that the galaxies in the cluster were moving much faster than expected based on the visible matter alone. To account for this discrepancy, he proposed the existence of missing mass, what we now refer to as dark matter. Further evidence came in the 1970s when astronomer Vera Rubin studied the rotation curves of spiral galaxies. Rubin found that stars at the outer edges of galaxies were moving just as fast as stars closer to the center, a puzzling result because, according to Newtonian mechanics, the stars on the outskirts should be moving slower if only visible matter was present. The explanation for this anomaly was that an unseen mass, dark matter, was providing the necessary gravitational pull to keep those stars moving at such high speeds. While dark matter has been established as a critical player in the universe's evolution, its composition remains a mystery. One prevailing theory suggests that dark matter is made of WIMPs, for weakly interacting massive particles. These hypothetical particles would interact with regular matter only through gravity and the weak nuclear force, making them difficult to detect. Despite several experiments designed to catch a glimpse of WIMPs, including underground detectors and particle accelerators like the Large Hadron Collider, LHC, none have yet provided definitive evidence. Another theory posits that dark matter could be composed of axions, ultralight particles that might also interact weakly with ordinary matter. Like WIMPs, axions have eluded detection, but ongoing experiments continue to search for them. There are also alternative explanations for dark matter's gravitational effects. Modified Newtonian dynamics, also known as MOND, is a theory that suggests the laws of gravity might need to be tweaked to explain galaxy rotation curves without invoking dark matter. However, MOND struggles to explain the full range of cosmological observations, such as the cosmic microwave background and the formation of large-scale structures in the universe, where dark matter plays a central role. Despite its invisibility, Dark matter is essential to the universe's structure. It acts like an invisible scaffolding upon which galaxies form and grow. Without dark matter, the early universe's matter density wouldn't have been enough to pull together into galaxies and clusters through gravity alone. Furthermore, dark matter's gravitational effects are critical in the study of cosmic phenomena, like gravitational lensing, where massive objects bend light from distant sources. Observing these light-bending effects allows astronomers to map out where dark matter is located, even though it remains unseen. While dark matter explains the gravitational forces holding galaxies together, dark energy addresses a completely different mystery: the accelerating expansion of the universe. Rate. In the 1990s, two independent teams of astronomers were studying distant supernovae to measure the universe's expansion rate. They expected to find that the expansion was slowing down, as gravity from matter should be pulling everything back together. Instead, they found the opposite. The universe's expansion was accelerating. This was a shocking discovery, as it implied the existence of a new, unseen force that was pushing galaxies apart. To explain this unexpected acceleration, cosmologists introduced the concept of dark energy. However, dark energy is even more elusive than dark matter, and its nature remains largely speculative. One leading hypothesis is that dark energy is related to the cosmological constant, first introduced by Albert Einstein. In his theory of general relativity, Einstein included a term called the cosmological constant, which acted as a repulsive force to counteract gravity and keep the universe static. After Edwin Hubble's discovery of the expanding universe, Einstein abandoned the idea, calling it his greatest blunder. However, the discovery of the accelerating universe brought the cosmological constant back into play as a potential explanation for dark energy. In this context, dark energy could be thought of as a property of space itself. As space expands, the energy density associated with dark energy remains constant, leading to the universe's accelerated expansion. This model fits current observations well, but it leaves many questions unanswered. For example, why does dark energy have the value it does? If the cosmological constant were slightly different, the universe might have expanded too rapidly for galaxies to form, or it might have collapsed in on itself. Another possibility is that dark energy is related to a dynamic field known as quintessence, which evolves over time. Unlike the cosmological constant, quintessence would change its strength as the universe expands, potentially providing a more flexible explanation for dark energy's effects. Dark energy is the dominant component of the universe, making up about 68% of its total energy density. Its influence has become more significant over time as the universe expanded. In the early universe, dark matter and radiation played a more prominent role, but as space grew larger, dark energy began to dominate, driving the accelerating expansion we see today. Dark energy has profound implications for the universe's fate. If the acceleration continues indefinitely, the universe will keep expanding, causing galaxies to drift farther apart. Eventually, distant galaxies may become so far removed that their light can no longer reach us, plunging the universe into a big freeze where stars burn out, and all that remains are isolated black holes and cold remnants of once luminous galaxies. Put simply, together, dark matter and dark energy make up about 95% of the universe's total content, but we know very little about their true nature. Neither dark matter nor dark energy is explained by the Standard Model or by general relativity, which suggests that our current understanding of the universe is incomplete. A true theory of everything must not only unify gravity with quantum mechanics, but also explain the existence and behavior of dark matter and dark energy. Thus, despite the progress made in theoretical physics over the past century, the quest for a theory of everything remains unfinished. Some physicists believe that new experimental discoveries, perhaps from high-energy particle colliders or precision measurements of cosmological phenomena, will provide the missing pieces of the puzzle. Others suggest that the very framework of physics may need to be radically rethought, requiring new concepts that go beyond space, time, and matter as we currently understand them. In the end, whether or not such a theory will ever be found remains an open question, but the pursuit itself has already deepened our understanding of the universe and our place within it. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. The neighborhood to the edge of time, the James Webb Space Telescope challenged our understanding of the cosmos and showed the universe in a way no other telescope in the past could. And in a recent remarkable observation, the $10 billion Infrared Space Observatory has focused on Mercury, which should already be a dead planet. Scientists thought the humble hunk of rock that's only slightly girthier than Earth's moon would have been battered to barrenness by the sun's intense solar radiation. It's a hostile world. The day and night sides of the planet see a temperature difference nearly 600 degrees Celsius. But Mercury has proved to be a world of contradictions, a dynamic planet that hides more surprises than scientists initially gave it credit for. And now, by using powerful telescopes like James Webb, scientists have once again lifted the veil on the secrets of the planet, revealing Mercury is not what we think. Join us as we shed light on the most enduring mysteries of the innermost planet in our solar system. Mercury is the closest planet to the Sun, orbiting at an average distance of about 57.9 million kilometers. With a diameter of just 4,880 kilometers, it is the smallest planet in the solar system, slightly larger than Earth's moon. Despite its proximity to the Sun, Mercury's surface temperatures vary dramatically, ranging from scorching highs of 430 degrees during the day to freezing lows of 180 degrees at night. Mercury's orbit is highly eccentric, meaning it is not a perfect circle, but rather an elongated ellipse. This eccentricity, combined with its rapid orbital period of just 88 Earth days, leads to fascinating orbital dynamics that have intrigued astronomers for centuries. One of the most notable features of Mercury's orbit is its 3-2 spin-orbit resonance, where the planet rotates 3 times on its axis for every 2 orbits around the Sun. The surface of Mercury is a stark, barren landscape, characterized by numerous impact craters, vast plains, and towering cliffs. The planet's surface bears the scars of a violent history, with craters ranging in size from tiny pits to massive basins hundreds of kilometers across. The largest of these is the Caloris Basin, a massive impact crater over 1,500 kilometers in diameter, formed by a colossal collision with an asteroid or comet billions of years ago. Mercury's surface is also home to a network of long, steep cliffs known as Lobat scarps. These scarps are thought to have formed as the planet's interior cooled and contracted, causing the crust to buckle and fracture. Some of these cliffs rise as high as 3 kilometers and stretch for hundreds of kilometers across the planet's surface. Despite its barren appearance, Mercury's surface is not entirely devoid of activity. Recent observations have revealed evidence of volcanic activity in the planet's past, with smooth plains and ancient lava flows suggesting that Mercury once had a more geologically active history. However, unlike Earth or Venus, Mercury's volcanic activity appears to have ceased billions of years ago, leaving behind a frozen, lifeless landscape. One of the most puzzling aspects of Mercury is its magnetic field. Mercury is the only terrestrial planet besides Earth to have a global magnetic field, although it is much weaker than Earth's. The existence of this magnetic field was first confirmed by NASA's Mariner 10 spacecraft in the 1970s, but its origin remains a mystery. A planet's magnetic field is typically generated by the motion of molten iron within its core, a process known as the dynamo effect. However, given Mercury's small size and proximity to the Sun, scientists were surprised to find that the planet still has an active dynamo. Theories suggest that Mercury's core may contain a higher proportion of iron than previously thought, or that the planet's core has a unique composition or structure that allows it to sustain a magnetic field. Adding to the mystery is the fact that Mercury's magnetic field is not symmetrical. It is significantly stronger in the northern hemisphere than in the southern hemisphere, a phenomenon that is not yet fully understood. Some scientists believe that this asymmetry may be due to variations in the planet's core or mantle, while others suggest that it could be a result of interactions between the magnetic field and the solar wind. What's more, unlike Earth, Mercury has no significant atmosphere. Instead, the planet is surrounded by an extremely thin layer of atoms known as an exosphere. This exosphere is composed primarily of oxygen, sodium, hydrogen, helium, and potassium, and is constantly replenished by the solar wind, micrometeoroid impacts, and the release of volatile materials from the planet's surface. The existence of Mercury's exosphere was first confirmed by Mariner 10 and later studied in greater detail by NASA's Messenger spacecraft. The exosphere is so tenuous that it is barely detectable, with an atmospheric pressure less than a trillionth of Earth's. Despite its thinness, the exosphere plays a crucial role in the planet's interaction with the solar wind and the space environment. One of the most fascinating aspects of Mercury's exosphere is its dynamic nature. The atoms in the exosphere are constantly being stripped away by the solar wind, only to be replaced by new atoms from the surface. This continuous exchange of particles creates a delicate balance that can be easily disrupted by solar activity, leading to fluctuations in the composition and density of the exosphere. Mercury's most striking feature is its unusually large core, which makes up about 85% of the planet's radius. This core is believed to be composed primarily of iron, with smaller amounts of nickel and other elements. The sheer size of Mercury's core relative to its overall size is unique among the terrestrial planets and has led to much speculation about the planet's formation and history. One of the leading theories suggests that Mercury may have once been a much larger planet, with a thick rocky mantle similar to Earth's. However, a giant impact early in the planet's history could have stripped away much of this mantle, leaving behind the dense metallic core we see today. This giant impact hypothesis is supported by the planet's high density and the relative scarcity of silicate materials on its surface. The core of Mercury is also thought to be partially molten, which may explain the planet's magnetic field. But the exact state of the core, whether it is completely liquid, partially solid, or something in between, remains an open question. Understanding the nature of Mercury's core could provide valuable insights into the formation and evolution of the inner planets in our solar system. However, given its proximity to the Sun and the extreme conditions on its surface, Mercury is a challenging planet to study. Mercury has been visited by only 2 spacecraft, NASA's Mariner 10 and Messenger missions. These missions have provided the bulk of our current knowledge about the planet, but what is really interesting about Mercury are the things that can't be seen. And now, thanks to incredible research efforts, scientists have finally given us some remarkable clues that could upend our understanding of this enigmatic world. In a groundbreaking revelation, scientists have discovered that Mercury, the innermost planet in our solar system, may harbor salt glaciers that could support life beneath its sun-scorched surface. This discovery is not only a significant leap in our understanding of the planet's geology, but also raises intriguing possibilities about the potential for life in environments once deemed inhospitable. The key to this new discovery lies in the data gathered by NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015. Messenger's suite of scientific instruments provided unprecedented insights into the planet's surface composition, magnetic field, and geological history. One of the most surprising findings from Messenger's mission was the detection of unusual surface features that suggested the presence of volatile substances, including water ice and salts. Researchers have long known that Mercury's poles contain deposits of water ice, trapped in permanently shadowed craters. These craters, located in the planet's polar regions, are shielded from the sun's harsh rays, allowing ice to accumulate and persist. However, the discovery of salt glaciers has added a new dimension to our understanding of Mercury's polar deposits. Analysis of Messenger's data revealed features that resemble glaciers on Earth, but with a twist. These so-called salt glaciers are formed from a mix of salts, such as sodium chloride and magnesium sulfate, and ice. The presence of these salt deposits suggests that, at some point in Mercury's history, liquid water may have been present on the planet's surface and subsequently evaporated, leaving behind these saline features. The formation of salt glaciers on Mercury involves several stages. First, volatile compounds such as water and various salts were likely present in the planet's crust. Over time, geological processes, including impacts and volcanic activity, would have brought these materials to the surface. When Mercury's surface temperatures fluctuated, especially in the shadowed regions near the poles, water ice could have formed and mixed with salts. The persistence of these salt glaciers is indicative of a complex climatic history. The planet's axial tilt is minimal, meaning that its poles receive very little direct sunlight. This, combined with the extremely low temperatures in the shadowed craters, has allowed these glaciers to remain relatively stable over geological timescales. The discovery of salt glaciers on Mercury prompts a re-evaluation of the planet's potential to support life. While the current conditions on Mercury are inhospitable to life as we know it, the presence of salts and ice raises the possibility that microbial life could exist in subsurface environments, similar to how life is hypothesized to survive beneath the icy crusts of moons like Europa and Enceladus. In addition to the presence of water ice and salts, the idea that Mercury once had a more temperate climate further fuels speculation about its potential for life. If liquid water was once stable on the surface, it opens up the possibility that life could have had a chance to develop during that period. Even if no evidence of life is found, these findings can provide valuable insights into the planet's geological history and the processes that shaped its surface. Another remarkable discovery: recent scientific research has unveiled a breathtaking possibility. Mercury might be hiding a treasure trove unlike anything we could have imagined, a diamond layer 15 kilometers thick. To understand how Mercury could host such an incredible deposit of diamonds, we first need to appreciate the planet's unique geological and environmental conditions. As told, Mercury is a planet of extremes. With temperatures fluctuating from a blistering 400 degree during the day to a bone-chilling 180 degrees at night, the surface is subject to tremendous thermal stress. This temperature variation alone suggests that the planet's surface could be a breeding ground for complex chemical reactions. Additionally, Mercury's lack of a substantial atmosphere, unlike Earth's thick blanket of air, leaves it exposed to the harsh solar wind, a constant stream of charged particles from the sun. These factors combine to create an environment where only the toughest materials can endure. This leads us to the key ingredient in our story: carbon. We all know that carbon is an essential element in the formation of diamonds. Under the right conditions, extreme pressure and temperature, carbon atoms can rearrange themselves into a crystal structure, creating diamonds. On Earth, diamonds are formed deep within the mantle, where pressures are immense. They are then brought to the surface through volcanic eruptions encapsulated in kimberlite pipes. But Mercury's formation and evolution took a different path. Recent studies suggest that Mercury's formation was marked by a cataclysmic event. During the early days of the solar system, a massive impact stripped away much of Mercury's outer layers, leaving it with an unusually large core relative to its size. This event could have also compressed large amounts of carbon deep within the planet, creating conditions ripe for diamond formation. Unlike Earth, where tectonic activity and erosion constantly reshape the surface, Mercury's geological activity is limited. This means that any diamonds formed in its early history could have remained largely undisturbed, accumulating over billions of years to form a thick layer. The idea of a 15-kilometer thick diamond layer on Mercury might sound like science fiction, but it's grounded in solid scientific principles. If Mercury's early history did involve massive impacts and intense pressure, it's plausible that much of the planet's carbon was converted into diamonds. Over time, as Mercury cooled and solidified, these diamonds could have settled into a stable layer beneath the surface. Moreover, Mercury's proximity to the Sun means it has been bombarded with meteoroids for billions of years. These impacts could have further driven carbon deep into the planet's crust, adding to the growing diamond reservoir. Some scientists hypothesize that the upper crust of Mercury could be a mix of regolith and diamond-rich rock, with the diamonds concentrated at deeper levels where pressures were once highest. One might wonder how such an extraordinary claim could be substantiated. The challenge lies in the fact that Mercury is not an easy planet to study. Its proximity to the Sun makes it difficult for telescopes to observe, and sending spacecraft to Mercury presents its own set of challenges. However, the Messenger spacecraft, which orbited Mercury from 2011 to 2015, provided a wealth of data that has since been analyzed to offer clues. Messenger's X-ray and gamma-ray spectrometers detected higher-than-expected levels of carbon on Mercury's surface, particularly in certain regions. This carbon, found in the form of graphite, could be the remnant of a once more extensive carbon layer that has since been weathered down by meteoroid impacts and solar wind. If graphite exists in significant quantities, it strengthens the case for diamonds lying beneath, as graphite and diamond are different forms of carbon. Moreover, the high radar reflectivity observed in some of Mercury's craters is another piece of evidence. Radar signals bounce back strongly from highly reflective surfaces, such as ice or metal. However, diamonds are also excellent reflectors of radar waves, meaning that these bright spots on Mercury's radar map could be hinting at diamond-rich areas. Regardless, to fully understand the implications of these discoveries, future missions to Mercury are crucial. The next major mission to Mercury is Bepi-Colombo, a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA. Launched in October 2018, Bepi-Colombo is currently en route to Mercury, with its arrival scheduled for December 2025. This mission is named after Giuseppe Bepi Colombo, an Italian scientist who first explained the relationship between Mercury's rotation and its orbit around the Sun. Bepi-Colombo consists of two spacecraft, the Mercury Planetary Orbiter, or MPO, developed by ESA, and the Mercury Magnetospheric Orbiter, or MMO, developed by JAXA. The two spacecraft will work in tandem to study Mercury's surface, interior, exosphere, and magnetosphere in unprecedented detail. The MPO will focus on the planet's surface and interior, mapping its topography, composition, and geological features, while the MMO will study the planet's magnetosphere and its interaction with the solar wind. One of the key objectives of Bepi-Colombo is to build on the discoveries made by Messenger. and answer some of the lingering questions about Mercury. For example, Bepi Colombo will investigate the origin of Mercury's magnetic field, which is much weaker than Earth's, and is likely generated by a partially molten core. The mission will also study the composition of the planet's surface, including the mysterious hollows, bright, shallow depressions that appear to be unique to Mercury. In addition to its scientific goals, Bepi Colombo will test advanced technologies that could be used in future missions to Mercury and other planets. For example, the mission's solar electric propulsion system, which uses ionized xenon gas to generate thrust, could pave the way for more efficient space travel in the future. While Bepi Colombo represents the next significant step in Mercury exploration, scientists are already looking ahead to future missions that could build on its findings. These missions could take various forms, from orbiters and landers to sample return missions, and even human exploration. One of the most exciting prospects for future Mercury exploration is the idea of sending a lander to the planet's surface. A lander would provide an unprecedented opportunity to study Mercury's geology up close, analyze its surface composition, and conduct experiments that are not possible from orbit. For example, a lander could drill into the surface to study the planet's interior structure or deploy instruments to measure the heat flow from the interior to the surface, which could provide clues about the planet's thermal evolution. However, designing a lander capable of surviving Mercury's extreme conditions presents significant challenges. The lander would need to be equipped with a sophisticated thermal control system to protect it from the intense heat of the sun, as well as radiation-hardened electronics to withstand the harsh environment. Additionally, landing on Mercury's surface is no easy feat given the planet's low gravity and lack of atmosphere, which makes it difficult to slow down the descent. Despite these challenges, there have been several proposals for Mercury lander missions. One such proposal is the Mercury Surface Element, also known as MSE, a concept developed by ESA as part of the Bepi Colombo mission. Although the MSE was ultimately not included in the mission, the concept could serve as the basis for future lander missions. Another proposal is the Mercury Lander Mission concept, developed by NASA's Jet Propulsion Laboratory, or JPL, which envisions a lander equipped with a suite of scientific instruments to study the planet's surface and interior. Another ambitious goal for future Mercury exploration is the return of samples from the planet's surface to Earth. A sample return mission would allow scientists to conduct detailed analyses of Mercury's surface material in laboratories on Earth, providing insights that are not possible with remote sensing or in situ measurements. For example, scientists could study the isotopic composition of Mercury's rocks to learn more about the planet's formation and evolution, or search for traces of volatile elements that could shed light on the history of water on the planet. Designing a sample return mission to Mercury poses several technical challenges. The spacecraft would need to carry a lander capable of collecting samples, as well as a return vehicle to bring the samples back to Earth. The mission would also need to overcome the challenges of operating in Mercury's extreme environment, as well as the difficulties of launching a spacecraft from the planet's surface. Despite these challenges, advances in technology and lessons learned from previous sample return missions, such as NASA's OSIRIS-REx mission to the asteroid Bennu, could make a Mercury sample return mission feasible in the future. While human exploration of Mercury is still a distant prospect, it is not entirely out of the realm of possibility. Advances in space technology, such as nuclear thermal propulsion and advanced life support systems, could one day make it possible for humans to visit Mercury and conduct scientific research on the planet's surface. Human missions to Mercury would likely be similar in scope to the Apollo missions to the Moon, with astronauts landing on the surface for short durations and conducting experiments before returning to Earth. Human exploration of Mercury would offer several unique opportunities for scientific research. For example, astronauts could conduct geological surveys of the planet's surface, study its magnetic field and interaction with the solar wind, and search for signs of past or present water. Additionally, human missions to Mercury could serve as a stepping stone for future exploration of other planets in the inner solar system, such as Venus or Mars. The future missions to Mercury have the potential to revolutionize our understanding of the planet and its place in the solar system. By studying Mercury's surface, interior, atmosphere, and magnetosphere in greater detail, scientists hope to answer key questions about the planet's formation and evolution, its geological history, and its interaction with the Sun. One of the key scientific objectives of future Mercury missions is to understand the planet's unique composition. Mercury has a much higher metal content than any other planet in the solar system, with a large iron core that makes up about 85% of its radius. This unusual composition has led scientists to propose several theories about Mercury's formation, including the possibility that the planet was once much larger and lost much of its outer layers in a giant impact. Future missions could provide the data needed to test these theories and determine the true origin of Mercury's composition. Another important objective is to study Mercury's magnetic field and its interaction with the solar wind. Unlike Earth, Mercury's magnetic field is weak and highly variable, with frequent reconnection events that create intense bursts of radiation near the planet's surface. By studying these phenomena in greater detail, scientists hope to gain insights into the dynamics of planetary magnetic fields and their role in protecting planets from solar radiation. Future missions could also shed light on the history of water on Mercury. Although the planet is thought to be too hot for liquid water to exist on its surface, MESSENGER discovered evidence of water ice in permanently shadowed craters at the poles. Bepi Colombo and future missions could study these ice deposits in greater detail, potentially revealing clues about the sources of water in the inner solar system and the history of volatiles on Mercury. Finally, future missions to Mercury could help answer fundamental questions about the formation and evolution of the solar system, and by extension, offer clues about the conditions that led to the formation of Earth and other terrestrial planets. One of the most intriguing aspects of Mercury is its unusually high metal content. The planet has an iron-rich core that accounts for about 85% of its radius, which is proportionally much larger than Earth's core. This composition suggests that Mercury experienced a different formation and evolutionary history compared to the other terrestrial planets. Understanding why Mercury is so metal-rich could shed light on the processes that influenced planetary formation in the early solar system. There are several hypotheses about Mercury's high metal content. One theory suggests that Mercury might have formed from material that was metal-rich from the beginning, possibly as a result of the Sun's early influence. Another hypothesis proposes that Mercury originally had a silicate-rich mantle similar to Earth's, but a massive impact during its formation stripped away much of this mantle, leaving behind a metal-rich core. Studying Mercury in detail could help scientists determine which of these scenarios is more accurate, providing insights into the conditions that existed in the inner solar system during its formation. Mercury is the only other terrestrial planet besides Earth that has a significant magnetic field, although it is much weaker than Earth's. The presence of this magnetic field suggests that Mercury has a partially molten outer core, which generates the field through the dynamo effect. By studying Mercury's magnetic field, scientists can learn more about the planet's core dynamics and how its magnetic field has evolved over time. Understanding Mercury's magnetic field could also provide clues about the early magnetic history of Earth. Earth's magnetic field is crucial for protecting our planet from solar and cosmic radiation, making it a key factor in the development and sustenance of life. By comparing Earth's magnetic field with Mercury's, scientists can gain a better understanding of the factors that influence magnetic field generation in terrestrial planets and how these fields evolve. This knowledge could also help scientists predict the future behavior of Earth's magnetic field, which is currently weakening. Mercury's surface is heavily cratered, similar to the Moon, but it also has unique features such as large cliffs or lobate scarps that run for hundreds of kilometers. These scarps are thought to have formed as Mercury's core cooled and contracted, causing the planet's surface to shrink and buckle. The presence of these scarps suggests that Mercury's geological history is still active, albeit at a much slower rate than on Earth. Studying Mercury's surface features can provide insights into the planet's geological history and the processes that have shaped its surface over billions of years. For instance, understanding the formation of lobate scarps can help scientists learn more about the thermal evolution of Mercury's core and mantle. This, in turn, can offer clues about the thermal histories of other terrestrial planets, including Earth. Mercury also has regions known as smooth plains, which are believed to be the result of ancient volcanic activity. The presence of these plains suggests that Mercury had a more geologically active past than previously thought. By studying the volcanic history of Mercury, scientists can learn more about the planet's internal heat generation and how it has changed over time. This information could be valuable for understanding the volcanic history of Earth and other terrestrial planets, as well as the role of volcanism in planetary evolution. Mercury has a tenuous atmosphere, or exosphere, composed mainly of hydrogen, helium, oxygen, sodium, and potassium. Unlike Earth's thick atmosphere, Mercury's exosphere is constantly being replenished by particles from the solar wind, surface interactions, and outgassing from the planet's interior. Studying Mercury's exosphere can provide valuable information about the interactions between the solar wind and planetary surfaces. The study of Mercury's exosphere is particularly important because it offers a unique opportunity to observe how a planet's surface and atmosphere interact with the solar wind. Since Mercury is so close to the Sun, it experiences much stronger solar wind conditions than Earth. By understanding how Mercury's exosphere responds to these conditions, scientists can gain insights into the processes that shape planetary atmospheres in general. This knowledge can also be applied to Earth, helping scientists better understand how our planet's atmosphere interacts with the solar wind, and how this interaction has influenced Earth's evolution. Mercury's unique characteristics challenge many existing models of planetary formation. Traditional models suggest that terrestrial planets formed from the gradual accumulation of planetesimals in the protoplanetary disk. However, Mercury's high metal content, weak magnetic field, and unusual surface features suggest that its formation involved processes that are not fully explained by these models. Studying Mercury in greater detail can help scientists refine these models and develop new theories about planetary formation. For example, understanding why Mercury has such a large iron core relative to its size could provide insights into the role of giant impacts in planetary formation. Similarly, studying Mercury's magnetic field and geological history can help scientists develop more accurate models of how terrestrial planets evolve over time. Mercury offers a unique opportunity for comparative planetology, the study of planets by comparing their properties and histories. By comparing Mercury with Earth, scientists can identify similarities and differences that provide insights into the process that shaped both planets. For instance, both Mercury and Earth have metallic cores and magnetic fields, but the differences in their sizes, compositions, and geological histories can help scientists understand the factors that influence planetary evolution. One key area of comparative planetology is understanding the role of size in planetary evolution. Mercury is much smaller than Earth, which has significant implications for its thermal evolution, magnetic field generation, and geological activity. By studying these differences, scientists can learn more about how a planet's size influences its evolution and what this might mean for Earth. Another area of interest is the study of planetary atmospheres. While Earth has a thick atmosphere that supports life, Mercury's exosphere is extremely thin and constantly influenced by the solar wind. Comparing these two atmospheres can provide insights into the factors that determine atmospheric retention and composition, which are crucial for understanding the conditions necessary for life. Mercury's proximity to the Sun and its unique characteristics make it a valuable target for studying the early solar system's evolution. The planet's high metal content, weak magnetic field, and unusual surface features suggest that it has experienced processes that are not fully understood and that may have been more common in the early solar system. By studying Mercury, scientists can gain insights into the processes that influence the formation and evolution of the solar system as a whole. For example, understanding Mercury's formation and evolution could provide clues about the distribution of materials in the protoplanetary disk, the role of giant impacts in planetary formation, and the thermal histories of terrestrial planets. These insights could also help scientists better understand the conditions that led to the formation of Earth and other habitable planets. In short, while Mercury is a small planet with a big story to tell, its unique characteristics make it a key target for understanding the formation and evolution of the solar system, including Earth. By studying Mercury's composition, magnetic field, geological history, and exosphere, scientists can gain valuable insights into the processes that shaped our planetary neighborhood. These insights can help refine existing models of planetary formation and evolution, providing a clearer picture of how Earth and other terrestrial planets came to be. As we continue to explore Mercury, we are likely to uncover even more secrets about the early solar system and the forces that shape the world we live on today. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.
About quark gluon plasma?
That's bad. That's bad for physics. For the cosmic microwave background, the leftover radiation from the Big Bang.
But you would like something...
NASA has been at the forefront of space exploration and scientific discovery for decades. Its relentless pursuit of knowledge has unveiled a series of discoveries that have profoundly altered our understanding of the universe. From distant galaxies and black holes to the early moments after the Big Bang, NASA's missions have expanded the horizons of human knowledge, challenging existing paradigms and fostering new theories. Join us in today's episode as we dig deep into the most significant discoveries that have reshaped our comprehension of the cosmos. Number 1. The cosmic microwave background radiation, the afterglow of creation. One of NASA's most significant contributions to cosmology is the discovery and mapping of the CMB, for cosmic microwave background radiation. The CMB is the faint afterglow of the Big Bang, the primordial explosion that gave birth to the universe approximately 13.8 billion years ago. This discovery provided critical evidence supporting the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB was first detected by accident in 1965 by Arno Penzias and Robert Wilson, who won the Nobel Prize in Physics for their work. However, it was NASA's Cosmic Background Explorer, COBE, satellite, launched in 1989, that provided the first detailed map of the CMB. COBE's data confirmed that the CMB was almost perfectly uniform across the sky, with tiny fluctuations that represented the seeds of all the current structures in the universe, such as galaxies and clusters of galaxies. These tiny fluctuations in the CMB provided crucial insights into the early universe's conditions, helping to refine the Big Bang theory and leading to a better understanding of the universe's age, composition, and development. The COBE mission was followed by the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, both of which provided even more detailed measurements of the CMB. These missions allowed scientists to determine that the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, a mysterious force driving the universe's accelerated expansion. The discovery and study of the CMB have been foundational in cosmology, providing a baby picture of the universe that has shaped our understanding of everything from the nature of matter and energy to the ultimate fate of the cosmos. Number 2. The accelerating expansion of the universe, unveiling dark energy. In the late 1990s, one of the most groundbreaking discoveries in astronomy was made using data from NASA's Hubble Space Telescope. Scientists found that the expansion of the universe is not slowing down, as previously thought, but is actually accelerating. This discovery was a complete surprise and led to the introduction of the concept of dark energy, a mysterious force that permeates all of space and is driving the universe's accelerated expansion. The discovery was made by observing distant type Ia supernovae, which are exploding stars that can be used as standard candles to measure distances in the universe. By comparing the brightness of these supernovae at different distances, scientists found that distant galaxies were moving away from us faster than nearby ones, indicating that the universe's expansion rate was increasing over time. The implications of this discovery are profound. Dark energy, which is believed to make up about 68% of the universe, remains one of the biggest mysteries in modern physics. Its discovery has led to a fundamental shift in our understanding of the universe, suggesting that the cosmos could continue expanding forever, potentially leading to a big freeze where galaxies drift apart, stars burn out, and the universe becomes a cold, dark place. NASA continues to study dark energy through various missions, including the upcoming Nancy Grace Roman Space Telescope, which aims to explore the nature of dark energy by measuring the distribution of galaxies across cosmic time. The discovery of dark energy is a testament to the unexpected ways the universe continues to surprise us, challenging our theories and pushing the boundaries of our knowledge. Number 3. The discovery of exoplanets, expanding the search for life. One of the most exciting and transformative discoveries made by NASA in recent decades is the detection of exoplanets, planets orbiting stars outside our solar system. This search was revolutionized by NASA's Kepler Space Telescope, launched in 2009, which was designed to monitor over 150,000 stars in a small patch of the Milky Way galaxy. Kepler's mission was to look for tiny dips in a star's brightness that occur when a planet passes in front of it, a method known as the transit method. Kepler's results were astonishing. The telescope discovered over 2,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. These discoveries revealed that planets are not rare, but are common throughout the galaxy, with estimates suggesting that there are more planets than stars in the Milky Way. Among these exoplanets, several have been found in the habitable zone of their stars, the region where conditions might be right for liquid water to exist on a planet's surface, which is considered a key ingredient for life. One of the most famous of these is Kepler 186, an Earth-sized planet located in the habitable zone of its star. This discovery has profound implications for the search for extraterrestrial life, suggesting that there may be billions of potentially habitable worlds in our galaxy alone. The discovery of exoplanets has opened up a new field of astronomy, with NASA continuing to lead the search for life beyond our solar system. The Transiting Exoplanet Survey satellite, also known as TESS, launched in 2018, is continuing Kepler's work by surveying the entire sky for exoplanets. Meanwhile, the James Webb Space Telescope, JWST, launched in 2021, is poised to study the atmospheres of these distant worlds in unprecedented detail, searching for signs of life. The discovery of exoplanets has fundamentally changed our understanding of the universe, revealing that our solar system is just one of countless planetary systems scattered throughout the galaxy. It has also reignited the age-old question: are we alone in the universe? NASA's ongoing search for exoplanets and the conditions for life continues to bring us closer to answering this question. Number 4. The observation of gravitational waves, a new window into the universe. In 2015, scientists made the first direct observation of gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, such as the collision of black holes. This discovery, which confirmed a major prediction of Albert Einstein's theory of general relativity, was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, a project with significant contributions from NASA. Gravitational waves were first predicted by Einstein in 1915 as part of his theory of general relativity, which describes gravity as the warping of space and time by massive objects. However, detecting these waves proved to be an enormous challenge due to their incredibly faint nature. LIGO, which consists of 2 facilities in the United States, was designed to detect these minuscule ripples by measuring the tiny distortions they cause as they pass through Earth. The first detection of gravitational waves came from the merger of 2 black holes, each about 30 times the mass of the Sun, located over 1 billion light-years away. This event was named GWW-15914 and marked the beginning of a new era in astronomy, gravitational wave astronomy. The ability to detect and study gravitational waves has opened up a completely new way of observing the universe. Unlike light, gravitational waves are not easily absorbed or scattered, allowing them to carry information about the most violent and energetic events in the cosmos, such as black hole mergers, neutron-star collisions, and even events from the early universe. Since the first detection, LIGO, along with its European counterpart Virgo, has detected dozens of gravitational wave events, providing new insights into the nature of black holes, the structure of neutron stars, and the behavior of matter under extreme conditions. These observations have confirmed that black holes are common throughout the universe and have provided a new way to test the limits of Einstein's theory. Looking ahead, NASA is collaborating on LISA for the Laser Interferometer Space Antenna, a space-based gravitational wave detector that will be sensitive to a different range of gravitational waves than LIGO, potentially revealing new physics and shedding light on the most mysterious phenomena in the universe. Number 5. The exploration of Mars, searching for life on the red planet. NASA's exploration of Mars has been one of its most enduring and scientifically rewarding endeavors. Since the 1960s, NASA has sent a series of missions to Mars, each more sophisticated than the last, culminating in the recent Mars rovers, such as Curiosity and Perseverance, which have transformed our understanding of the red planet and its potential to host life. One of the most groundbreaking discoveries on Mars came from the Curiosity rover, which landed in Gale Crater in 2012. Curiosity found evidence that Mars once had conditions suitable for life, including ancient riverbeds, lakes, and the presence of key chemical ingredients for life, such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Curiosity also detected complex organic molecules in Martian soil, which, while not proof of life, are the building blocks of life as we know it. The Perseverance rover, which landed in Jezero Crater in 2021, is continuing this search for life. Jezero Crater was chosen as the landing site because it is believed to have once been a lake, with river deltas that could have preserved signs of ancient microbial life. Perseverance is equipped with advanced scientific instruments to analyze rocks and soil, searching for biosignatures, chemical or physical signs of past life. One of Perseverance's most ambitious goals is to collect samples of Martian rock and soil that will be returned to Earth by a future mission. This will allow scientists to study Martian material in unprecedented detail, potentially providing the first direct evidence of life beyond Earth. NASA's Mars exploration program has not only provided evidence that Mars was once habitable, but it has also laid the groundwork for future human exploration. For example, the discovery of water ice on Mars suggests that future astronauts could extract water for drinking and producing oxygen and rocket fuel, making long-term human missions to Mars feasible. As NASA prepares for the next steps in Mars exploration, including the potential human exploration of Mars in the 2030s, the discoveries made by missions like Curiosity and Perseverance will continue to be a vital foundation for our understanding of the red planet and its potential to support life. Number 6. The structure of the Milky Way. For centuries, the true shape and extent of the Milky Way remained elusive due to our position within it. However, through the use of advanced telescopes and space missions, NASA has unveiled the intricate details of the galaxy's architecture. The Milky Way is a barred spiral galaxy, characterized by a central bar-shaped region of stars and a disk composed of several spiral arms. These spiral arms, filled with gas, dust, and young stars, wind out from the central bulge, which houses older stars and a supermassive black hole known as Sagittarius A. The galaxy's disk is relatively thin, but it extends for about 100,000 light-years across, with the Sun located about 26,000 light-years from the galactic center, nestled in the Orion Arm. One of the most significant breakthroughs in mapping the Milky Way came from the NASA-led Cosmic Background Explorer, or COBE, and later, the Spitzer Space Telescope. COBE helped confirm the Milky Way's spiral structure by detecting the distribution of stars and dust in infrared light, which penetrates the dense interstellar dust that obscures visible light. Spitzer further refined this view, revealing the intricate details of the galaxy's arms and confirming the presence of the central bar. In addition, NASA's WMAP and the European Space Agency's Gaia mission have provided crucial data about the Milky Way's shape and size. Gaia, in particular, has mapped the positions and motions of over 1 billion stars, giving astronomers an unprecedented 3D view of the galaxy. This data has helped confirm that the Milky Way is not a simple disk, but has a warped shape, likely caused by interactions with neighboring galaxies, such as the Sagittarius Dwarf Galaxy. Moreover, NASA's Fermi Gamma-Ray Space Telescope has uncovered evidence of massive bubbles of high-energy radiation extending above and below the Milky Way's disk. These Fermi bubbles are thought to be remnants of an energetic event in the galaxy's past, possibly linked to activity from Sagittarius A. NASA's efforts to map and understand the structure of the Milky Way have not only expanded our knowledge of our galaxy, but have also provided insights into the processes that shape galaxies across the universe. This research continues to evolve, offering new glimpses into the dynamic and ever-changing nature of the Milky Way. Number 7. The exploration of the outer solar system. NASA's Voyager exploration of the outer solar system represents one of the most ambitious and successful endeavors in the history of space exploration. Launched in 1977, Voyager 1 and Voyager 2 were initially designed to take advantage of a rare planetary alignment that allowed them to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, using gravity assists to propel them from one destination to the next. This grand tour of the solar system provided humanity with its first close-up views of these distant worlds, fundamentally changing our understanding of the outer planets and their moons. Voyager 1 was the first of the 2 spacecraft to launch and quickly became the first human-made object to fly by Jupiter in 1979. The data it sent back revealed the planet's turbulent atmosphere, with its Great Red Spot, a massive storm larger than Earth, and its complex system of moons. Particularly significant was the discovery of active volcanoes on Io, one of Jupiter's moons, making it the first body beyond Earth known to be volcanically active. Voyager 1 then proceeded to Saturn in 1980, where it captured detailed images of the planet's rings and discovered new moons. It also provided a closer look at Titan, Saturn's largest moon, revealing its thick atmosphere, which scientists believe might harbor conditions similar to early Earth. Voyager 2 followed a similar path, but went on to achieve what no other spacecraft has done. It visited Uranus in 1986 and Neptune in 1989. The flyby of Uranus uncovered a magnetic field tilted at a bizarre angle and 11 new moons. Voyager 2's encounter with Neptune provided the first images of the planet's dynamic atmosphere, including the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, and the discovery of geysers on Triton, Neptune's largest moon. After completing their primary missions, both Voyager spacecraft continued on their paths out of the solar system, with Voyager 1 becoming the first spacecraft to enter interstellar space in 2012, followed by Voyager 2 in 2018. As of 2024, Voyager 1 is about 15 billion miles from Earth, and Voyager 2 is around 13 billion miles. These distances are vast, but the twins still send data back to Earth by using their onboard instruments and radio communication systems. The signals they send take over 20 hours to reach Earth, traveling at the speed of light. Despite their distance, the spacecraft continue to transmit valuable scientific information about the space environment they encounter as they journey through the outer reaches of the solar system and into interstellar space. The data they send back is helping scientists learn more about the heliosphere, the protective bubble created by the sun's solar wind, and the interstellar medium beyond it. This information is crucial for understanding how our solar system interacts with the surrounding galaxy and provides a glimpse into the conditions of interstellar space, a region that has remained largely unexplored until now. Number 8. The Hubble Deep Field and the Evolution of Galaxies. The Hubble Deep Field represents one of the most profound observational campaigns in the history of astronomy. Conducted by the Hubble Space Telescope in 1995, this initiative aimed to peer into the farthest reaches of the universe, revealing a patch of sky in the constellation Ursa Major that was seemingly empty and devoid of stars or galaxies. Over 10 consecutive days, Hubble captured light from this tiny region, about 1/24 millionth of the sky, creating an image that forever changed our understanding of the universe. The Hubble Deep Field revealed a staggering number of galaxies, nearly 3,000, in a minuscule portion of the sky. These galaxies varied greatly in shape, size, and color, indicating a broad spectrum of ages and evolutionary stages. Some of the galaxies were relatively close to Earth, while others were billions of light-years away, meaning Hubble was capturing images of these galaxies as they appeared when the universe was just a fraction of its current age. This unprecedented glimpse into the early universe offered astronomers crucial insights into the evolution of galaxies. The Hubble Deep Field provided a timeline that spanned billions of years, showing how galaxies have changed over cosmic time. Some of the most distant galaxies in the Hubble Deep Field were small and irregular, suggesting that they were in the early stages of formation. This observation supports the theory that galaxies began as small structures that merged and grew into the massive galaxies we see today, like the Milky Way. Moreover, the diversity of galaxies observed in the Hubble Deep Field, from spirals to ellipticals to peculiar shapes, helped scientists piece together the processes that drive galaxy evolution. For instance, the presence of blue, star-forming galaxies alongside older, redder galaxies indicated that star formation was more rampant in the early universe and has since slowed down. The Hubble Deep Field also highlighted the importance of dark matter in galaxy formation. The distribution and interaction of galaxies in the field suggested that dark matter played a crucial role in their evolution, influencing their shapes and the rate at which they merged with others. Overall, the Hubble Deep Field provided a window into the universe's distant past, offering a profound understanding of how galaxies evolve over time. It set the stage for future deep-field observations and remains a cornerstone in our quest to understand the origins and fate of galaxies in the cosmos. Number 9. The exploration of the Kuiper Belt and the discovery of Pluto's geology. The Kuiper Belt, a distant and icy region of the solar system, represents one of the last frontiers of planetary exploration. Located beyond Neptune's orbit, this vast donut-shaped disk is home to countless icy bodies, dwarf planets, and remnants from the early solar system. First proposed by astronomer Gerard Kuiper in 1951, the Kuiper Belt was hypothesized as a region containing small, icy bodies left over from the solar system's formation. It wasn't until the early 1990s that the first Kuiper Belt object was discovered, confirming the existence of this distant region. The Kuiper Belt extends from about 30 to 55 astronomical units from the Sun, with its objects composed primarily of frozen volatiles such as water, ammonia, and methane. The discovery of the Kuiper Belt provided critical insights into the origins of short-period comets and the early solar system's formation processes. As a reservoir of ancient material, the Kuiper Belt holds the potential to reveal secrets about the solar system's birth and the processes that led to the formation of planets. The most significant milestone in the exploration of the Kuiper Belt came with NASA's New Horizons mission. Launched in 2006, New Horizons was the first spacecraft designed to explore this distant region, with its primary target being Pluto, the most famous of the Kuiper Belt's inhabitants. After a journey of nearly a decade, New Horizons made its historic flyby of Pluto in July 2015, providing humanity with its first close-up images and data from this enigmatic dwarf planet. The flyby revealed Pluto as a complex and geologically active world, shattering previous assumptions that it was a frozen, inert body. New Horizons sent back images of towering mountains of water ice, vast plains of nitrogen ice, and signs of cryovolcanism. The mission's success highlighted the importance of exploring the Kuiper Belt, showing that even at the solar system's fringes, planetary bodies could be dynamic and diverse. Following its successful flyby of Pluto, New Horizons continued its journey deeper into the Kuiper Belt. On January 1, 2019, it made a close approach to another Kuiper Belt object, Arrokoth, previously known as 2014 MU69. This small, bilobed object provided scientists with a glimpse into the early solar system's building blocks. Arrokoth's shape and surface features suggested that it formed through the gentle merging of two smaller bodies, providing valuable insights into how planets and other solar system bodies might have formed. The exploration of Arrokoth and other Kuiper Belt objects has deepened our understanding of the Kuiper Belt as a repository of primordial material. These objects have remained largely unchanged since the solar system's formation, preserving the conditions of the early solar nebula. By studying them, scientists can gain a clearer picture of the processes that led to the formation of planets and the evolution of the solar system. On the other hand, note that the exploration of the Kuiper Belt is still in its early stages, with much left to discover. Future missions could target other Kuiper Belt objects, including larger and more distant objects, to further unravel the mysteries of this remote region. The Kuiper Belt also presents a valuable opportunity to study the formation of planetary systems in other star systems, as it shares similarities with the debris disks observed around young stars. Moreover, the continued exploration of the Kuiper Belt has implications for our understanding of the solar system's boundaries. The region marks the transition from the solar system's planetary zone to the more distant and diffuse Oort cloud, the source of long-period comets. Understanding the Kuiper Belt's structure and population is key to comprehending the solar system's architecture and its interaction with the interstellar environment. Number 10. The first images of black holes and the Event Horizon Telescope. Black holes has long fascinated scientists and the public alike, largely because of the enigmatic nature of their cosmic giants. They are regions of space-time where gravity is so intense that nothing, not even light, can escape. This makes them invisible against the backdrop of space, but their presence can be inferred from their effects on nearby matter and radiation. A groundbreaking tool in the study of black holes has been the Event Horizon Telescope, also known as EHT, an international collaboration that aims to capture images of these elusive objects. It could be said that the EHT represents a monumental leap forward in observational astronomy. The project began in earnest in 2012, bringing together over 200 researchers from institutions worldwide with the goal of imaging the event horizon of a black hole. The EHT is not a single telescope, but a network of radio telescopes located at different points around the globe. By synchronizing these telescopes through a technique called very long baseline interferometry, the EHT effectively creates a planet-sized observatory with unprecedented resolution. The EHT's first major achievement was the release of the image of the supermassive black hole in the galaxy M87 in April 2019. This was a historic moment in astrophysics, as it provided the first direct visual evidence of a black hole's existence. The image showed a bright ring-like structure with a dark central region representing the shadow of the black hole against the glowing gas and plasma surrounding it. This groundbreaking result confirmed many predictions of general relativity and provided new insights into the structure and behavior of black holes. The success of the EHT then has paved the way for further explorations into the nature of black holes. Future improvements in the array, including the addition of more telescopes and the use of higher frequency observations, are expected to enhance the resolution and detail of the images. Upcoming observations will focus not only on refining the image of M87's black hole, but also on imaging the event horizon of the black hole at the center of our own Milky Way galaxy, known as Sagittarius A. Additionally, the EHT's findings are likely to have broader implications for our understanding of fundamental physics. For example, studying the behavior of matter and radiation near the event horizon may provide insights into the nature of space-time, the formation of black holes, and the processes governing their growth and interactions with their surroundings. In summary, the study of black holes and the contributions of the Event Horizon Telescope represent a profound leap in our understanding of the universe. By capturing images of these cosmic behemoths, the EHT has provided a direct glimpse into regions that were previously beyond the reach of observational astronomy, opening up new avenues for research and deepening our understanding of the most extreme objects in the cosmos. Number 11. The James Webb Space Telescope and the Early Universe. The James Webb Space Telescope has opened a new era of cosmology. Launched on December 25, 2021, Webb's advanced capabilities have significantly transformed our comprehension of the early universe, providing unprecedented insights into the cosmos's infancy. At its core, Webb's ability to peer deep into the universe is facilitated by its large, segmented mirror and its position in orbit around the second Lagrange point, about 1.5 million kilometers from Earth. This strategic location, combined with its infrared-optimized instrumentation, allows the telescope to observe the faintest and most distant objects in the universe, those that were previously beyond the reach of earlier telescopes like Hubble. One of the most groundbreaking contributions of James Webb is its capability to observe the universe's first galaxies. By looking back in time through the infrared spectrum, the telescope can detect the light from the earliest galaxies that formed shortly after the Big Bang, about 13.8 billion years ago. These observations have provided new insights into the formation and evolution of the first galaxies. revealing that galaxy formation occurred much earlier than previously thought. For instance, James Webb has identified galaxies formed only a few 100 million years after the Big Bang, challenging previous models of galaxy evolution and pushing the boundaries of our knowledge about how these structures emerged. Webb's deep-field observations have also shed light on the process of reionization, a pivotal era in the universe's history when the first stars and galaxies ionized the intergalactic medium. This period marked the transition from the cosmic dark ages to a universe filled with light. By examining the distribution and characteristics of early galaxies, James Webb has provided crucial data on the timing and nature of reionization, offering a more detailed picture of how the first cosmic structures interacted with their surroundings and contributed to the reionization of the universe. Moreover, the observatory has made significant strides in understanding the formation of stars and planetary systems. Its high-resolution infrared imaging allows scientists to observe star-forming regions obscured by cosmic dust, revealing previously hidden details about the birth of stars and the formation of protoplanetary disks. These observations are crucial for understanding the processes that lead to the formation of planetary systems, including our own. By studying these early star-forming regions, James Webb helps bridge the gap between the initial formation of stars and the eventual development of planetary systems, offering insights into the conditions that might lead to habitable planets. Another critical aspect of James Webb's mission is its ability to study the physical and chemical properties of the early universe. Through its advanced spectroscopic capabilities, the Webb telescope can analyze the light from distant galaxies and stellar objects to determine their composition, temperature, and other fundamental properties. This information is vital for understanding the chemical evolution of the universe, including the formation of heavy elements and the enrichment of the interstellar medium. By examining the spectral signatures of early galaxies and stars, James Webb provides a detailed account of how these objects contributed to the chemical makeup of the universe. In addition to its observational capabilities, findings made by James Webb have prompted a re-evaluation of theoretical models of cosmic evolution. Its data has led to new hypotheses about the formation and growth of galaxies, the nature of dark matter, and the conditions that led to the development of complex structures in the universe. These insights are reshaping our understanding of cosmological processes and prompting revisions to existing models of the early universe. The impact of James Webb extends beyond the immediate realm of galaxy and star formation. Its observations have provided a broader context for understanding the fundamental processes that shaped the universe's structure. By offering a clearer picture of the early universe, the Supreme Observatory helps scientists address some of the most profound questions in cosmology, including the nature of dark energy, the formation of the first black holes, and the origins of cosmic inflation. In summary, thanks to its advanced observational capabilities and infrared technology, the Premier telescope has dramatically enhanced our knowledge of the cosmos's infancy. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. Some of the most impressive objects in our universe are supermassive black holes. Weighing in at millions, billions, or even tens of billions of solar masses, they're the heaviest single objects contained within the known universe. One of the great problems in modern astrophysics is the open question of how they formed and grew up, and in many ways, the dawn of the James Webb era has only intensified that problem. Looking back toward the dawn of time, we find supermassive black holes existed even very early on, reaching hundreds of millions or even a billion solar masses, by the time only a few 100 million years had elapsed, when the universe was just a few % of its current age. Was it just plain old astrophysics that led to their creation, with nothing special happening to seed them? Or is it possible that the universe was actually born with seed black holes that would rapidly grow into the supermassive behemoths we observe much later on? Or does James Webb just find some hints of our previous universe? All this and more will be discussed in today's episode. Let's start with one relevant plot that we can look at as our starting point. A plot of the inferred black hole masses in these early galaxies from when the universe was around 5% of its current age versus the total mass inferred to be in the form of stars. The reason this plot is important is that today, when we plot the more typical black hole to stellar mass ratio of galaxies, as shown in the gray shaded regions, we get a value that's more typically around 0.1%, indicating that earlier on, galaxies may have had more massive black holes compared to the amount of stars inside. For example, take the black hole at the center of the galaxy Messier 87, one of the largest, most massive, and brightest galaxies within 100 million light-years of our own. It contains within it an enormous supermassive black hole, one that weighs in at 6.5 billion solar masses, or some 1,500 times as massive as the Milky Way's largest black hole. But it also contains an enormous number of stars, around 1 trillion of them, with an estimated stellar mass of around 2.4 trillion solar masses. The supermassive black hole to stellar mass ratio for this galaxy, which contains the largest supermassive black hole in our vicinity, still only comes in at a paltry 0.27%. If central supermassive black holes and galaxies formed together and grew up together, we'd expect that ratio to remain relatively constant over time. As galaxies grow and grow, so would their supermassive black holes, keeping pace with one another. However, the possibility that many would love to consider is that perhaps the universe didn't form early black holes and early stars concurrently, and that those two components of the galaxy grew up together. Instead, perhaps the universe was born with a set of primordial black holes, or black holes that formed in the immediate aftermath of the hot Big Bang, and then those black holes served as nucleation sites for galaxies to form around and grow. However, there are two other ways to make black holes in the universe that fall within the standard history scenario that don't involve primordial black holes, or black holes formed in the immediate aftermath of the Big Bang at all, but merely conventional astrophysics. Instead of being born with black holes, the universe could have simply been born with normal, slight density imperfections, tiny fluctuations that result in initially overdense and underdense regions. Those overdense regions could slowly grow, attracting more and more matter, until one of two things occurs. First, stars can form from this matter, resulting in massive stars that burn through their fuel quickly and die, with their cores collapsing and resulting in seed, black holes of tens, hundreds, or maybe even up to 1,000 solar masses. Second, cold streams of gas can fall into these overdense regions and collide with one another, which could form stars like normal. However, alternatively, it could lead to a phenomenon known as direct collapse, where the matter becomes dense enough in a small enough volume of space that black holes can directly form, leading to a population of much heavier black hole seeds in the range of tens of thousands or even hundreds of thousands of solar masses. The first one definitely happens, but the second one could happen as well, and requires no new physics to trigger it, unlike the primordial black hole scenario. Although it might not seem like a big deal, the difference between a primordial black hole, a stellar mass black hole, and a heavy seed formed via direct collapse is extremely significant. When we're looking at galaxies in the very early universe, we're seeing the universe as it was an incredibly long time ago, more than 90% of the universe's history ago. Even back prior to the James Webb era, we were finding galaxies with large, massive black holes that were comparable to 1 billion solar masses from when the universe was between 650 and 800 million years old, just 5 to 6% of its current age. Now, in order for a black hole to get that big that fast, it must have grown up quickly. Based on the physics that we know, there's a limit to how quickly a black hole can grow from devouring matter, the Eddington limit. If we extrapolate from the black holes we observe at those early times, but not super early times, back to the very early universe, we find that if we go back to when we expect the first stars to form and the first streams of cold gas to collide, we're looking at time periods when the universe was just 50 to 150 million years old, and we can infer the size and mass of the seeds we need. It turns out that one of the options, to invoke a standard astrophysics and stellar mass black hole seeds, also known as light seeds, is ruled out by the data. The situation only worsened in the James Webb era, as the record for earliest supermassive black hole was pushed back earlier and earlier. In July of 2023, Webb's researchers from the Sears collaboration reported the discovery of Sears 1019, which contains a black hole of 9 million solar masses from an age of 570 million years, representing 0.1% of the stellar mass inside the galaxy. Then, a few months later, a galaxy known as U8Z1 was found, at an age of 470 million years, with a rather large black hole mass of 10-100 million solar masses, but with a small stellar mass content also between 10-100 million solar masses, where the black hole is 10-100% of the stellar mass content of the galaxy. And galaxy GN Z11, as shown in January of 2024, contains a supermassive black hole of 1.53 million solar masses, just 420-440 million years after the Big Bang, although its stellar mass content is large at close to 1 billion solar masses, and it appears to be undergoing super Eddington accretion right now. In other words, what we're seeing suggests a mix of light and heavy seeds as the origin of supermassive black holes, but doesn't suggest a need for even earlier, truly primordial black holes. Seeds of 10,000 to 100,000 solar masses are completely sufficient for everything we see, even if those initial black hole seeds didn't arise until up to 150 million years after the Big Bang. However, the direct observation of what we call overmassive, or in some corners, outsized black holes, such as UHZ1, and also, as suggested more weakly by the more recent Ruby's paper, rules out the light seed scenario very thoroughly, as a team led by Fabio Picucci predicted would occur back in 2017. If you begin with heavy, black hole seeds that are driven by cold streams of colliding gas and forming via a direct collapse mechanism, you'd expect to find overmassive black holes early on, and you'd expect that to be the norm. With black hole to stellar mass ratios of Shakur 10 to 100% in early low-mass galaxies, of 110% later on in more massive, more evolved galaxies, of 0.1 to 1% in still more evolved galactic populations, and then declining to the more standard 0.1% as seen in present-day galaxies. In a compilation of James Webb-observed galaxies from the first 1.5 billion years of cosmic history, Picucci's team was able to show precisely this predicted evolutionary trend, using galaxies primarily extracted from Webb's Sears, JADES, and GLASS observing programs. Although there are still uncertainties on these values, they strongly suggest a heavy seed formation mechanism, as the below graph illustrates. So what, then, of the primordial black hole scenario? The issue is twofold. If you want to form primordial black holes, your universe needs to be born with enormous magnitude overdensities, or regions where the density is more than number 68% greater than the cosmic average density. If you have a region that's more overdense than that, you can prove that it will, in fact, collapse rapidly to form a black hole, and that's the primary scenario by which you can form primordial black holes that will persist until the present day. Unfortunately, there are two reasons that such a scenario is strongly disfavored. The first comes from direct observations of the universe, which give us a series of constraints concerning how much matter, out of the total amount of normal and dark matter combined, is allowed to be in the form of primordial black holes of varying masses. At low masses, that is below the mass of a typical large asteroid, black holes that were born at the start of the hot Big Bang would have evaporated, and the lack of that evaporative radiation rules them out. From about moon mass objects to brown dwarf masses, direct searches for microlensing events rule out more than a few percent of the mass being in the form of black holes. But for heavier masses, from the lowest stellar masses on upward, the lack of gravitational wave signals, the lack of accretion signals, and the lack of features appearing in the CMB, also known as the cosmic microwave background, strongly constrain the abundance and presence of these heavier mass primordial black holes. If we wanted to create primordial black holes that were great enough in mass to serve as seeds for the black holes we observe in the late-time universe, they would have to be at least 100 solar masses in magnitude back when they were first created. However, that's just about the threshold that would mess up the fluctuations in the cosmic microwave background. It's a very challenging scenario to create them. But there's a second, arguably even stronger reason to disfavor the emergence of a large population of primordial black holes. Remember, to create a black hole primordially, in the aftermath of the Big Bang, you need an enormous initial overdensity, something that's 68% greater in density than average. But we already know the spectrum of overdensities in the universe from cosmic inflation. It has a large-scale amplitude of just c-03%, and that amplitude drops as we move to smaller and smaller cosmic scales. The only way to produce such a population is with a finely tuned phase transition. This transition could have occurred at the end of inflation at the electroweak scale during the formation of protons and neutrons, or during some yet undiscovered transition later on. However, this requires that we have a spike of giant magnitude overdensities, about 68% or more, at one particular mass, and then at all other scales, the overdensities are just of that standard ρ-0-3% value. It's not only a highly constrained scenario from observations, it's one where you have to contort your theory tremendously to produce the primordial population of black holes you desire. So, at the end of the day, could the supermassive black holes we see have arisen from a population of primordial black holes that sprang into existence in the extremely early stages of the hot Big Bang? The real answer is that it's a scenario that is neither supported nor favored by the data, but that isn't completely ruled out just yet either. It is plausible that higher resolution studies of the CMB can place stronger constraints on such a scenario, but the most promising line of evidence to find out for sure will be to push the cosmic limits even farther, looking for galaxies with black holes in them even earlier in the universe's history, from the first 150-400 million years. If the heavy seed scenario is the right one, this should be the place to look to confirm it. In addition, James Webb might be able to help, but deep observations in other wavelengths of light, such as X-ray wavelengths, would be ideal. X-rays are a form of electromagnetic radiation with much shorter wavelengths and higher energy than visible light. They are produced by extremely hot and energetic processes in the universe, such as the accretion of matter onto black holes, supernova explosions, and the collision of galaxies. X-ray emissions, particularly in the case of black holes, often originate from the regions just outside the event horizon, the so-called accretion disk, where gas and dust spiral inward, heating up to millions of degrees as they fall toward the black hole. Observing the universe in X-ray wavelengths allows astronomers to study phenomena that would otherwise remain invisible to optical telescopes. Black holes, for instance, emit little to no light directly, but their presence can be inferred by detecting the intense X-ray radiation from their surroundings. Thus, X-ray astronomy serves as one of the most crucial tools in the study of black holes, particularly ancient and distant black holes, which may hold the keys to understanding the early universe. Current space telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton have been instrumental in advancing our knowledge of black holes. They have provided astronomers with detailed X-ray observations of both stellar mass black holes and supermassive black holes at the centers of galaxies. However, these observatories are limited in their ability to explore the most distant and ancient black holes due to their sensitivity and resolution constraints. The X-ray emissions from black holes that formed in the early universe are faint and difficult to detect, often drowned out by other cosmic sources. Moreover, while these observatories have significantly advanced our understanding of how black holes interact with their environments, such as by ejecting jets of material at near-light speeds or by influencing star formation rates in their host galaxies, there is still much we don't know. The formation of the first black holes, their role in the evolution of the early universe, and the mechanisms by which supermassive black holes grew so quickly in the first billion years after the Big Bang remain unanswered questions. But upcoming missions aim to bridge this gap and offer new insights into the early universe's most massive and mysterious objects. The Athena, also known as Advanced Telescope for High-Energy Astrophysics mission, scheduled for launch by ESA in the late 2030s, is set to be the next major leap in X-ray astronomy. Athena will have unprecedented sensitivity, allowing it to detect X-ray emissions from some of the earliest and most distant black holes in the universe. By capturing faint X-rays emitted by black holes at high redshifts, meaning from a time when the universe was less than 1 billion years old, Athena will provide insights into how the first black holes formed and evolved. Athena's Wide Field Imager and X-ray Integral Field Unit will offer high-resolution observations of black holes and their surroundings. These instruments will help astronomers study black hole feedback, the process by which black holes regulate star formation and heat up the gas in their host galaxies. By observing black hole feedback in galaxies at various stages of their evolution, Athena will shed light on the complex relationship between black holes and their host galaxies. Another future mission, NASA's proposed Lynx X-ray Observatory, is designed to complement and surpass the capabilities of current X-ray telescopes. Lynx aims to have 100 times the sensitivity of Chandra, making it one of the most ambitious space telescopes in development. If funded and built, Lynx would be able to detect individual black holes forming just hundreds of millions of years after the Big Bang. Lynx's high-resolution X-ray imaging will allow astronomers to map the environments around supermassive black holes in distant galaxies, offering clues to how these objects grew so rapidly in the early universe. One of the major questions Lynx aims to answer is whether these ancient supermassive black holes formed from the direct collapse of massive gas clouds, or whether they grew from smaller seed black holes over time. Moreover, Lynx will allow astronomers to study the population of intermediate mass black holes, those between stellar mass and supermassive black holes, whose existence has long been theorized but remains elusive. These intermediate mass black holes could represent a key stage in the growth of supermassive black holes, and their detection would help bridge the gap in our understanding of black hole formation and growth. The future of X-ray observations will also be closely linked to the rise of multi-messenger astronomy, the coordinated observation of cosmic events using multiple types of signals, including gravitational waves and electromagnetic radiation. Black holes are prime targets for multi-messenger observations because their mergers, for instance, produce both gravitational waves and X-ray emissions. Gravitational wave observatories like LIGO and Virgo have already detected several black hole mergers, but the combination of these signals with X-ray observations will offer a more complete picture of black hole evolution. When a black hole merger occurs, X-ray telescopes like Athena or Lynx could observe the aftermath, revealing how the newly merged black hole interacts with its surroundings. This will provide astronomers with a unique opportunity to study black holes in real time. In short, as we look to the future, it is clear that the next generation of X-ray observatories will play a crucial role in uncovering the secrets of black holes, especially those that formed in the early universe. With missions like Athena and Lynx on the horizon, we are poised to explore the most distant and ancient black holes ever detected. These observations will not only help us understand the formation and growth of black holes, but will also shed light on the broader processes that shaped the evolution of galaxies and the universe itself. By pushing the boundaries of X-ray astronomy, scientists hope to answer fundamental questions about the origins of supermassive black holes, the nature of dark matter, and the dynamics of cosmic evolution. The next decades of exploration will likely reshape our understanding of black holes and provide a more complete picture of the universe's history. In the meantime, let's take a quick look at recent observations of black hole. Using the Hubble Space Telescope, astronomers have discovered the closest massive black hole to Earth ever seen, a cosmic titan frozen in time. As an example of an elusive, intermediate mass black hole, the object could serve as a missing link in understanding the connection between stellar mass and supermassive black holes. The black hole appears to have a mass of around 8,200 suns, which makes it considerably more massive than stellar mass black holes, with masses between 5 and 100 times that of the Sun, and much less massive than aptly named supermassive black holes, which have mass millions to billions that of the Sun. The closest stellar mass black hole scientists have found is called Gaia BH1, and it sits only 1,460 light-years away from us. The newly found intermediate mass black hole, on the other hand, dwells in a spectacular collection of about 10 million stars called Omega Centauri, which sits around 18,000 light-years from Earth. Interestingly, the fact that the frozen black hole appears to have stunted its growth supports the idea that Omega Centauri is the remains of an ancient galaxy cannibalized by our own galaxy. This would suggest Omega Centauri is actually the core of a small, separate galaxy whose evolution was cut short when the Milky Way swallowed it. If this event had never happened, this intermediate black hole may have possibly grown to supermassive status, like the Milky Way's own supermassive black hole, Sagittarius A, which has a mass 4.3 million times that of the Sun and is located 27,000 light-years from Earth. That discovery is so important because these intermediate mass black holes with masses between a few hundred and a few thousand times that of the Sun have, for the most part, seemed to have avoided detection. That's because, like all black holes, these mid-sized cosmic titans are marked by outer boundaries called event horizons. The event horizon is the point at which the gravitational influence of a black hole becomes so immense that not even light is fast enough to escape it. Thus, black holes are only visible in light if they are either surrounded by matter to feed on, which glows while heating up, or rip apart and feed on an unfortunate star in a so-called tidal disruption event. Intermediate black holes, like the one in Omega Centauri, aren't surrounded by a lot of matter and feeding. That means astronomers have to be a little bit cunning when hunting for such black holes. They use the gravitational effects these voids have on matter, like stars that orbit them, or on light passing through them. This new discovery's team used the former method. The hunt for this intermediate black hole began in 2019 when Nadine Neumeyer of the Max Planck Institute for Astronomy, or MPIA, and Anil Seth of the University of Utah designed a research project to improve our understanding of Omega Centauri's formation history. In particular, the researchers and collaborator Maximilian Heberle, an MPIA PhD student, wanted to find rapidly moving stars in Omega Centauri that would prove the star cluster has a massive, dense, or compact central engine black hole. A similar method was used to determine the mass and size of SGR-8A using a fast-moving population of stars at the heart of the Milky Way. Haberle and team used over 500 Hubble images of this star cluster to build a vast database of the motions of stars in Omega Centauri, measuring the speeds of about 1.4 million stars. This ever-repeating view of Omega Centauri, which Hubble conducted not out of scientific interest, but rather to calibrate its instruments, was the ideal dataset for the team's mission. Looking for high-speed stars and documenting their motion was the proverbial search for a needle in a haystack. The team ultimately found not one, but 7 needle-in-haystack stars, all moving at rapid velocities in a small region at the heart of Omega Centauri. The rapid speed of these stars is caused by a concentrated mass nearby. If the team had only found one rapid star, it would have been impossible to determine whether its speed was the result of a large and close central mass, or if that star is a runaway moving at a rapid pace in a straight path, absent of any central mass. Spotting and measuring the different velocities and directions of 7 stars allowed this determination to be made. The measurements revealed a centralized mass equivalent to 8,200 suns, while visual inspections of the region revealed no objects that resemble stars. That is exactly what would be expected if a black hole was located in this region, which the team determined to be light months wide. The fact that our galaxy has matured enough to have grown a supermassive black hole at its heart means it has probably outgrown the stage of possessing many intermediate mass black holes of its own. This one exists in the Milky Way because the cannibalization of its original galaxy happened to curtail its growth processes. Of course, that doesn't really change the status of SGR-A as the closest supermassive black hole to Earth, or Gaia BH1's status of the closest stellar mass black hole to Earth. But it provides some reassurance that scientists are on the right track when considering how our central black hole became such a cosmic titan in the first place. Elsewhere on Earth, an experiment using beams of protons to probe how plasma and magnetic fields interact may have just solved the mystery of how quasars and other active supermassive black holes unleash their relativistic jets. Let's picture the scene at the heart of a quasar. A supermassive black hole, perhaps hundreds of millions, or even billions, of times the mass of our sun, is ravenously devouring matter that is streaming into its maw from a spiraling, ultra-hot disk. That charged matter is called plasma, and it gets gravitationally drawn into the black hole's surroundings. However, not all of the plasma, which is made from ionized or electrified atoms shorn of electrons, is swallowed by the black hole. Indeed, the black hole bites off more than it can chew, and some of the plasma is spat out in jets collimated by the black hole's powerful magnetic field before that plasma gets anywhere near the event horizon, which is basically the point of no return. These jets can stretch thousands of light years into space. However, explaining the physics that takes place at the base of the jet, where they're formed, has eluded scientists. The answer may have come from researchers at the Princeton Plasma Physics Laboratory, or PPPL, in New Jersey, who were able to devise a modification to a plasma measuring technique called proton radiography. In their experiment, the researchers first created a high-energy density plasma, by firing a pulsed 20-joule laser beam at a plastic target. Then, they used powerful lasers to instigate nuclear fusion in a fuel capsule filled with deuterium and helium-3. The fusion reactions released bursts of protons and X-rays. These protons and X-rays then passed through a nickel mesh filled with tiny holes. Think of the mesh as like a colander for straining pasta. It strains the protons into many discrete beams that then can measure how the expanding plasma plume interacts with a background magnetic field. Because the protons are charged, they'll follow the magnetic field lines as they are buffeted by the plasma. The X-ray burst acts as a check. Because the X-rays pass cleanly through the mesh and the magnetic field, they provide an undistorted image of the plasma to compare to the proton beam measurements. As Will Fox, the experiment's principal investigator, said in a statement, "Our experiment was unique because we could directly see the magnetic field changing over time. We could directly observe how the field gets pushed out and responds to the plasma in a type of tug-of-war." They observed in detail the magnetic field bending outward under pressure from the expanding plasma, with the plasma sloshing against the magnetic field lines. This bubbling and frothing of the plasma is known as magneto-Rayleigh-Taylor instability, and it created shapes in the magnetic field that look like whorls and mushrooms. Crucially, as the plasma energy decreased, the magnetic field lines were able to snap back. This compressed the plasma into a straight, narrow column, not unlike a quasar's relativistic jet. According to PPPL's Sophia Malko, when we did the experiment and analyzed the data, we discovered we had something big. Observing magneto-Rayleigh-Taylor instabilities arising from the interaction of plasma and magnetic fields had long been thought to occur, but had never been directly observed until now. This observation helps confirm that this instability occurs when expanding plasma meets magnetic fields. The experiment strongly indicates that quasar jets can thank this sort of reaction of magnetic fields to the expanding plasma for their creation. If the results are a snapshot of what happens around active black holes, that would mean, in the black hole's accretion disk, conditions become so intense that the plasma in the disk is able to push against the tightly packed magnetic field lines, which can then snap back and push the plasma into a narrow column, almost squirting it away from the black hole. If true, this might be a huge missing piece in our picture of how active black holes operate. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.